Раз, 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 раз. Приходит? Ра- запоздало просто. Нормально.
All right.
Now it's working.
All right. So
Now
am
I'm
I? Yes.
1, 2, 3. 1, 1, 2, 3. Yes.
Testing. Sounds good.
So I think I can do it without this weird kind of amplifier, acoustic amplifier. Not very good. Very aggressive. So we have two guests today.
Okay, excuse me, you just because we are recording.
Okay. Sorry. Okay. Then I'll be obedient. And as everyone knows, and actually Alex Tikhonov knows very well, Alex, I'm not obedient. Am I right? Thank you so much. So anyway, to the point. So Nazarbayev University, as you well know, has established a physics department. Also, he is moving along to establish two extremely large operations. One in accelerator physics, and Alex Tikhonov is leading that effort. And another one, about the universe. And Aliyah is leading this effort. And we have actually recruited a Nobel Prize winner with his team to work with us to do a world-class laboratory here. And as you well know, George Smoot got his Nobel Prize when he was at Berkeley, but then he spent substantial amount of time in Paris, in Moscow, in Korea, and now he's in Astana. So this team is bringing a tremendous amount of experience of establishing world-class research in different parts of the world. So I'm really impressed how they managed to deal with fresh bureaucracy. Okay, guys, I'm impressed. So that's spectacular. So they are giving us a try. They will try to establish, as I said, a world-class laboratory here in this campus. And they are completely open, as they told me, to collaborate with everyone who cares to do high quality physics, astrophysics, computing, or anything else. And today it's a one-day kind of event that Eric is going to lead. And we have Professor Kazumi from very interesting places to give us a beautiful kind of talk. And I think it's time to start.
Well, thank you very much. So, thank you, Professor Kobanis, for the very excellent introduction. So, I have my own microphone. I don't need this. Okay, very good. So the program today is in the morning. I'm going to give an introduction to cosmology, and in particular some of the most recent research on the accelerated expansion of the universe and what is called dark energy. And this will lay the conceptual framework then for the afternoon talk by Professor Hazumi, who's going to talk about using the relic radiation from the Big Bang, the cosmic microwave background, to probe not only the recent universe, but all the way back to the first tiny fraction of a second after the Big Bang. So my talk is going to be very introductory to lay all the concepts out, and then Professor Hazumi will be talking about some of the very exciting research that has been going on. I know that we are going to be having students both from Nazarbayev University and from some of the other universities here, and so I've pitched my talk to lay out the concepts for the students, and I know we also have faculty from areas of physics and engineering and science that are not as familiar with cosmology, and so again, hopefully I want everyone to be able to understand the various concepts so that then Professor Hazumi's talk, you will really appreciate the excitement of probing back the 14 billion years of history in the universe. I also particularly want to thank the visitors who have traveled through the wind and the snow to come here from other universities in Kazakhstan. And they've traveled, for example, from Almaty, 1,000 kilometers away. And this is an excellent opportunity to lay out the scales that we're talking about when we talk about the universe, the cosmic scales. So 1,000 kilometers is 10 to the 8th centimeters. So we're going to take that scale of 10 to the 8th centimeters, and now go a factor of 1,000,000 more than that. And so think how long it took you to get here from Almaty, how long a distance that is, those sort of human scales. And now we go a factor of 1,000,000 greater, and we get to scales of the solar system, the planets. And of course, that's extremely exciting science, the exploration of the solar system. So that's a step 1,000,000 up from the journeys that you've made today. As we then go out to the galaxy, that's not 1,000,000 times, that's 10,000,000 times greater a scale. And so the universe is getting to be a pretty big place. As we move from galaxies out to the universe, to what Energetic Cosmos Laboratory is studying, we have another factor of 10,000,000. Your journey to the solar system, another factor of 10,000,000 to the galaxy, another factor of 10,000,000 out to the universe.
Sorry.
Yes?
Sorry. Tell me please, when it is possible to ask you questions after your lecture or during this lecture?
I think it is good to ask during the lecture, yes. Very definitely. Okay?
So my first question is,
Mm-hmm.
By the way,
remember we had this Friday discussion saying that some of us are interested in the analogs of the black holes of tabletop experiment.
Yes.
So have you guys been thinking if we can really match these kinds of let's say time scales or space scales in a mock-up laboratory? And we have tiny machines on the top of the pin of something, the 59, for example, ideas of Richard Feynman?
So that's an extremely interesting question in that we've learned that as we explore gravity, for example, so is on tests of them or actually on laboratory scales down to tens of micron scales, because there is this duality, this relationship between what happens on the largest scales and what happens on smaller scales. I will not have the opportunity to talk about that today, but yes, this is an extremely interesting area of scientific research. Yeah. So these are what I call the realms of the cosmos. Energetic Cosmos Laboratory focuses on those very largest scales of the universe. Out to the Milky Way galaxy, and this, for example, shows planets be habitable? Could life have arisen on any of these other planets as well? And so the sort of exciting questions you get when you explore solar system and the galaxy, we have equally exciting questions on the very largest scales of the universe. Because we've talked about such an extrapolation, a factor of 1,000,000 to the solar system, another 10,000,000 to the point that we can actually do some of those tests within the laboratory. And so we can understand physics in the laboratory and be able to apply it out to the universe. And that's very important. But there are other ways that we can learn things at a distance without traveling to another star, without traveling out into the universe. And so the three main ways that we learn about the universe is through observations from telescopes on the ground. So this shows telescopes in Hawaii on the top of a tall mountain, Mauna Kea. And this shows a satellite, the Planck satellite, which studies the cosmic microwave background. Professor Hazumi will be talking about the cosmic microwave background this afternoon. There's thinking hard about something, understanding the principles of physics on Earth and applying it to the universe. And so, of course, Einstein was the paragon of thinking hard about the universe and being able to predict how the universe behaves, and then the observations verified that. So his theories of special relativity, general relativity were tested in the laboratory and in the cosmos and worked very well. And then a more modern approach is computation and simulation, using very high performance computers to simulate aspects of the universe and to test out the theories and the observations that way. Energetic Cosmos Laboratory will use all three of these approaches to explore the universe, to become part of international surveys and make observations, to have very clever people who can think very hard, apply the principles of physics, and also use advanced statistics, machine learning, deep learning, computation to understand the universe as well. And so again, for the students in the audience, there are many different ways that you can contribute to the physics in the department, in the National Laboratory, in Energetic Cosmos Laboratory. So again, it still seems strange, these many factors of a million that we go out into the universe. How can we be sure that we understand the universe at such vast distances? And this is not a new question. So back 180 years ago, there was a very famous French philosopher, Comte, who said, how can we ever know anything about the stars? We can't touch the stars. We can't go out to the stars and probe into the stars. How can we possibly know what stars are made of? And the incredible, wonderful thing about science is there are clever people around who can take a seemingly impossible question and find an answer. And the other incredible thing about science is how quickly it happens that people are able to do this. So it was only 14 years later that a German physicist, Kirchhoff, came up with the solution how we can know the composition of stars. He discovered that by splitting light up into its energy spectrum, the same way that a rainbow, a prism splits up light, but with more sophisticated instruments with higher resolution, we can learn about the composition of objects, that there's a unique fingerprint for every element. So we can see helium in the sun, we can see carbon in stars, that we can understand this without traveling to the stars, without breaking them open. But the light comes to us naturally, we analyze that light. Spectroscopy, that energy spectrum, can tell us about objects at a distance. And this is not so unfamiliar. So if we walk into a supermarket in a strange country, we see some can, and we read the label and we say, okay, well, I walk into a supermarket here and I say, okay, I can't read the Russian label, I can't read the Kazakh writing, what's inside it? Each item comes with what's called a universal product code, right? It has a series of dark and light lines. And that universal product code tells exactly what is inside. Maybe I can't read it with my eyes, but the laser scanner at the checkout counter when I go to pay for it says exactly what is inside, how much it costs, and so forth. And that's exactly what the energy spectrum of light provides. And so as we look at the sun, we break up its light into the rainbow of colors in the visible. We have these dark and light lines, emission lines, absorption lines, and that tells us the chemical elements that make up the object. We don't only need to do that to our sun, we can do that to distant stars in the galaxy, to stars in other galaxies, to quasars, to incredibly distant objects that are 10 billion light years across the universe. We can still understand what they are made of by looking at their energy spectrum. And so this idea that the only way you can learn something is by breaking it open in the laboratory is not true. Light, the physics of radiation can tell us exactly what an object is made of. I'm going to go back further. So this was 180 years ago. I'm going to go back much further. I'm going to go back a few thousand years. And there's a very famous story that all of you may know, that there was a king in ancient Greece, and he wanted a beautiful crown made. And so he gave a certain quantity of gold to his goldsmiths, to the artisans, and he said, make me a beautiful crown. And they came back with this beautiful crown. But he was a very suspicious king, and he said, how do I know that it's really solid gold, that they used all the gold I gave them and they didn't hide some of the gold away, and they only put gold on the outside. Have they cheated me? How can I possibly know? And if a scientist in his court went to him and said, oh, break it open and see if it's solid, that scientist would not stay around the court very long. Science needed to develop a way to look inside an object, to understand what an object is made of, without breaking it. How do we know about the contents of it? And so there was a very famous scientist called Archimedes, again, many of you may know this story, who understood, how do I figure out what is the density, what is the interior composition of that object? So it's very hard to measure the volume of the object because it's such a strange shape. Volume of a cube, I can measure that. Volume of a sphere, I can measure that. How do I know the volume of that? If I want to know the density of an object, I can weigh it to get its mass, but I have to divide by its volume to get its density and see, does it have the same density as gold? And Archimedes, in the famous story, realized that when he lowered himself into his bath, that an amount of water ran out corresponding to the volume that he was displacing. And so he took the crown, immersed it in a bath of water, measured the volume of water that came out, and he was able to figure out what the density of the crown was. And yes, it was solid gold. The king was not cheated. So science is a very useful thing in understanding what an object is made of. Let's make this a little bit more modern. So now we go up to the 1960s, and we're going to use the same principle that Archimedes used for the crown. And the question was, the Great Pyramids in Egypt, are there secret tombs, secret treasure rooms hidden inside of those pyramids, or are they solid? So this sounds just like the situation with the gold crown. Are these solid, or are there spaces in there? Are there different densities inside there? And we didn't have Archimedes, but we had a very, very clever physicist, Luis Alvarez at Berkeley, who eventually won the Nobel Prize, not for this, but for many interesting things he did in particle physics, who said, again, we have naturally occurring particles in the universe, in the cosmos, called muons, that are passing through objects all the time. And there's a very good group right here at Nazarbayev University who studies cosmic ray particles and looks at their spectrum of energy and understands how they interact with the atmosphere. So the group of Professor Beznosko here is doing something very similar to this, trying to learn about the universe along the way. And so Professor Alvarez realized that if he could put a detector under the pyramid, that he could measure the density of the pyramid as these particles came in from different directions. And if there was a hole, if there was a treasure room somewhere, the density would be less in that direction. And he would be able to say, the density is different over here, and then you don't have to break apart the pyramid. You just look in that one little area to see, is there an empty space? Is there a tomb or a treasure room? And so Luis Alvarez was very clever experimental physicist. He always learned how to think about these things.
That's a little bit of a social tidbit.
Yes.
The experiment that Alvarez did, how many people would have? The experiment that he did to get the Nobel Prize.
Oh, so the Nobel...
The Nobel Prize experiment, how many people?
That's right. So he won his Nobel Prize for understanding resonances in particles, how particles interact with each other. And back in the 1960s, teams would be half a dozen people. Okay? You would just get your expert friends together, and you would say, okay, I need someone who is expert in counting particles. I need someone who is expert in understanding how materials work. So he used what's called a bubble chamber. And so you have some engineers who build the bubble chamber, someone who understands how the material works, someone who can track the particles. But you don't need teams of hundreds or thousands of people. Science has changed to a large extent, but there are still these small groups. So for example, the group I mentioned, the cosmic ray group of Professor Beznosko here, again, he has many students, but it's really him and a few people. So you can do great science with small groups. You can also do great science with large groups. And a good mix of these things is important, I think, to do science. So the idea behind the Higgs boson was, again, half a dozen people. But to find the Higgs boson was several thousand people. Yes. So you need this mix. Yes. So again, this is how we can do the science of the universe without looking into a star directly without going to a different galaxy. We use the natural particles, the light and the cosmic ray, high energy particles, the cosmic microwave background to learn about the universe the way it is and the way it was. And that's an important thing, that we can probe in time as well as space. So in a very real sense, astronomy is a time machine. So think, nobody sends postcards anymore. Everyone just texts on their phone. So this analogy doesn't work as well as it used to. But I think you all remember postcards at least. A friend travels on vacation and they send you a postcard saying, oh, I'm at the beach. It's so warm here. You don't know that it's warm right then. It was warm when they sent the postcard, several days before. And the further away they traveled, the longer it took the postcard to get to you. And so they're telling you about the conditions further and further in the past as they're at a greater distance. And that's exactly what we have in the universe. That light takes a certain amount of time to travel to us. So the further out we look in the universe, we're also looking further back in time and probing the conditions far back in the universe. And so astronomy lets us look into the past of the universe. What was the early universe like? Again, what Professor Azumi will talk about is just the first fraction of a second after the Big Bang, almost 14 billion years ago. And we can know that because we can measure the light that traveled to us that entire distance. So again, we can learn about cosmic history even though we can't touch the objects that are out there. Light comes to us and brings us those messages. So in a very similar way that we can learn about the conditions on the Earth in the past by looking at the rings in trees, we look at a very old tree and we can see, oh, this year had a very narrow ring. Maybe it was very cold or very dry and the tree didn't grow so much. This year had a very wide growth ring. And so maybe the conditions were very good for the tree. It was warm or it was wet. So we can learn about the past through the relics that come to us. Cosmology is exactly the same way. We look at the stars, the galaxies, and we can measure how quickly the universe was expanding at different times, how quickly the universe as a whole was growing from the light that comes to us from the objects. So again, we can measure basically the expansion history, the cosmic history of the universe in this way. And here's a picture taken by the Hubble Space Telescope, looking 10 billion years back in the past. Basically, all of these tiny, tiny little dots that you see are full-size galaxies, or nearly full-size galaxies, the way they existed 10 billion years ago. So again, we're looking back into the past. Now let me turn a little bit to the theory. Remember I said you want observations, you want theory, and you want computation to learn about the universe. So let me talk about the thought, how we can understand how the universe expands, what makes it expand. And there's one very, very simple principle that Einstein formulated at the beginning of the 1900s that basically gives us all the answers to understand how the universe works. He called it the equivalence principle. And you can write it down very simply. You don't need equations, you don't need tensor matrices or anything like that. You can write it down in words and you can get the right answer. And so gravity, the force of gravity, is equivalent to the curvature of space-time, and I'll explain what that means, and it's equivalent to an acceleration. We're very familiar with accelerations. You sit in a car, you step on the gas pedal, the car goes from standing still to gaining some velocity. It changes its velocity, it accelerates. There's a force. You feel the force pushing you back in the seat. You're in an elevator, it goes up, you feel the acceleration. So acceleration measures a force. Gravity is a particular type of force. And now we have this strange geometric concept of space-time curvature. And Einstein said these are all actually the same things. So the force which changes the motions of particle can be also thought of as the particles moving in a space-time geometry. Again, in the physics department here at Nazarbayev University, we have people who think very deeply about this. And what does it mean when the gravity becomes so extreme that you form black holes? How does the space-time curve in that extreme situation? How do the particles move under these situations? What happens to a star when it collapses under a very strong force of gravity, these compact objects? So we have faculty members, Professor Good, Professor Malafarina. We have excellent researchers here thinking about these questions related to this universe overall. So here is exactly the Einstein equivalence principle in pictures. If I'm standing in an elevator and I have a ray of light that enters one part of the elevator, if the elevator is accelerating upward, that ray of light curves and it will hit the other wall of the elevator as the elevator moves up in a different location. Now suppose I have a ray of light going on the surface of the Earth. The gravity of the Earth bends the path of the light. And now let me put it in a space-time. Again, the path of light will curve as the space-time is curved. So these are all exactly the same thing. They are equivalent, says Einstein. Okay. So I won't go through this in detail. I've basically said what's going on, that whether the force is due to gravity bending the light or whether it's due to some acceleration on the elevator, then the path of light is the same. And that if I'm in a small region, I can't tell the difference. They are equivalent. Now, what about the space-time curvature? How does that come in? That's a little less intuitive. And so we're going to do a thought experiment. Einstein was very good at thought experiments. So this is a space-time diagram. I'm going to ask, how does a particle move in space on the vertical axis, and how does it move in time on the horizontal axis? So here I have an atom, and this atom is going to give off a pulse of radiation. It's going to give off a flash of light. It's sitting here. It's not changing its location in space, but a certain time later, it's going to give off another flash of light. In a space-time diagram, light travels on 45-degree angles. It goes equal amounts of space as time. So that defines a 45-degree angle. So each flash of light travels on 45 degrees. So if you remember your high school geometry, if I've got a horizontal line and I have two 45-degree angles, those are parallel, I must have a parallelogram. And so this top part should be equal in length to the bottom part. So now let's actually carry the experiment one step further and say, suppose there was some acceleration. What happens then? Well, if there's an acceleration, you know that's a change in velocity. And so the velocity is simply the acceleration g times the amount of time over which that acts. So the amount of time it acts is simply the height divided by the speed of light, how much time the light ray traverses. So the acceleration g causes a velocity. We know about Doppler shifts. We know that if there's a Doppler shift, that changes the frequency of light. But the frequency of light is just the inverse of the period. So if I flash every second, then my period is 1 over 1 second. Okay? But if there's an acceleration, there's a velocity, there's a Doppler shift, and so I should get a shift in the frequency, which means I should get a shift in the time, of order this. Again, g is the acceleration. But I'm not accelerating. I'm in gravity. But I learned on the last slide that acceleration and gravity are the same. So if an acceleration gives me a Doppler shift, gravity must give me a frequency shift as well. And that's called a gravitational redshift. So that's changing the frequency, changing the time. And that says that t prime does not equal t0. So what went wrong with everything I learned in high school in geometry? Does any of the students know the answer? So what went wrong is your high school geometry was talking about flat space. It was talking about Euclidean geometry. And the only solution to this puzzle is that space cannot be flat. That when you have an acceleration or when you have gravity, that must mean that space acts like a curved surface. You cannot be Euclidean geometry. And so your parallel lines basically do not give you a parallelogram anymore. And so this is Einstein's equivalence principle. Acceleration equals gravity equals space-time curvature. So it's a very simple concept with very deep implications. So now let's bring this out into the universe. Yes.
This was the Eddington experiment. This is the first confirmation that there is bending of light.
So that's bending of light. The changing of the frequency, the gravitational redshift, was done in 1960 by Pound and Rebka.
Correct, but
Yes.
the first one was 1919 or 29.
Well, the Eclipse expedition
Yes.
was in 1919, right?
So 1919 and then the Pound Repa in 1960.
Yes, exactly.
And what is today's state of the art of this measure?
So gravitational redshift can be measured extremely accurately. What is the accuracy on it? So,
That's okay. I mean, that's the we check the book.
I think it's something like 10 to the minus 11
And
accuracy.
which group has this?
So they use the Mossbauer resonances to do this, so they
that's
get
right.
very narrow resonance lines. I know there was a group in Moscow that was working on this in after Redka in the 70s. I don't know who has the world record accuracy
Okay.
currently.
So essentially, it's 1919, the first measurement, 1960,
Right.
and
And then there've been-
and 1970. Let's say the
Right.
next step.
But there's many other tests of relativity, the binary pulsar, the emission of gravitational radiation. Again, Professor Azumi will talk about gravitational waves as part of general relativity. Yeah. So as we go out into the universe, we have to have a way of describing the curvature of space-time because that's describing gravity. That's describing the expansion of the universe. So you take the Pythagoras theorem. Okay. I don't know, do we have any pens to write on the board? You all know the Pythagoras theorem. X squared plus y squared, right? The sum of the sides of a right triangle gives you the length of the diagonal. X squared plus y squared gives you the diagonal squared. That's flat space. You have to generalize that. Instead of x squared plus y squared, you have some function times x squared plus some function times y squared. And that function, those coefficients, are called the metric of that space-time. So here we've written it in spherical coordinates, and all you have to know about cosmology as a whole is that there are two functions that enter in front of the coordinates. There's this extra a as a function of time, and then there's this extra constant k that changes just our normal spherical coordinates. It gives us something in the denominator. So there's one constant number, which relates to the spatial curvature. And then there's one function of time, which is called the scale factor. You see, it comes in front of all the spatial coordinates. So it just scales the universe. That says the universe is not static, but it's expanding in time or contracting. And observations have to tell you which one of those it is doing. So we're not going to go into general relativity, tensor calculus, all of that here. Again, there are excellent people in the physics department who give courses, who will do research on this. For cosmology, we can actually be extremely simple. So the special cases are when k equals 0. That means that space is flat. But Einstein taught us we have to think about space and time together, space-time. And space-time flatness says a double dot equals 0. So again, a question for the students. When a quantity has two time derivatives, what do we call that? If we have a position and we have one time derivative, that gives us what quantity? Velocity, two time derivatives, acceleration. This is Einstein's equivalence principle. When the acceleration is 0, then the space-time curvature goes away because they're equivalent. See how simple cosmology is? Einstein was just so clever, saw so deeply, that he was able to say something in 3 words, gravity equals acceleration equals space-time curvature, that we can learn all about the universe from that. So as I say, this is exactly the equivalence principle. So the overall way we describe our universe then is we start with the equivalence principle, and that tells us we have to have this description of space-time curvature. That is, we have to have some metric. How do we choose what the right metric is? We make observations of the universe and we say, the universe seems to be very simple. It looks roughly the same in all directions when we look at the very largest scales. Again, Professor Azumi will talk about how the cosmic microwave background makes an excellent test of this isotropy, that it looks almost exactly the same in all directions. It also looks almost exactly the same in large volumes. If you take a large volume of air in this room over here, a large volume of air in the room over there, it's roughly the same. The air is roughly homogeneous throughout the room. In the universe, again, the conditions in different parts of the universe are very similar. And that simplifies this metric description to just these two quantities, this Robertson-Walker metric with A and K. Okay? We then have to add a specific theory of gravity, general relativity, and that gives us specific equations of motion called the Friedmann equations. Russian physicist Alexander Friedmann, who first wrote these down in the early 1920s. And then we have to say something about the contents of the universe. How much matter is there? How much radiation is there? Are there neutrinos? Are there other particles? We have to give some experimental input as well. I'll skip over this slide. Again, all the slides are going to be posted. Again, if you are clever enough, if you're an excellent physicist, you're able to take all these complicated equations and put them into simple sentences that really capture all of the information. So yes, you can do general relativity in tensor notation, but you can also say it in some very simple words that if you understand the words well enough, you know how to do the calculations. Yes?
What was your grade?
So as I mentioned here, there are 3 different ways of doing general relativity. You can do it in tensor calculus ways. You can do it as a field theory, using group theory basically, and you can do it in differential geometry. I actually took general relativity 3 times. I took it with excellent teachers in each one of these. And you learn so much by viewing the same subject in different ways. So you think you know a subject, try to teach it. That's an excellent way of seeing, do you understand the subject? Try to explain it to someone else. If you can explain it simply, that means you're an expert. If you think you're an expert, but you can't explain to someone else, well, how does it work? You're not as much of an expert as you thought you were.
Excuse me, I have a question.
Yes.
In previous slide.
Mhm.
Again, previous.
Okay.
There was about energy momentum has a perfect fluid form. What's it mean?
I'll get to that in a few slides explaining exactly what that means. Basically, what it means is there's only 2 quantities that you have to understand, the energy density and the pressure. Okay, again, it's a very simple description. The reason it's so simple is because the universe is very simple. It has this great symmetry of isotropy looking the same in all directions and homogeneity looking the same in different volumes. Okay, so again, all the slides are going to be online, so I want to get to some of the exciting research at the end to lead into Professor Hazumi's talk. So I'm going to skip over most of this very quickly. This is just showing how all that general relativity, tensor calculus, differential geometry basically reduces down to Newton's second law to understand how the universe evolves. So we're really applying Newton's laws to the universe with slight changes. So Newton's law basically says, here's the inverse square law of gravity. The acceleration goes as the inverse square of the distance because of gravity. And I'm going to change the mass over to a density. So a density is just the mass divided by the volume. The real equation that you get from general relativity looks extremely similar, except we see that instead of just the density, we have to add 3 times the pressure. So there's a relativistic generalization because pressure contributes to the effective mass. So that's something beyond what Newton understood. Einstein extended Newton. But that gives a very interesting implication in that suppose the pressure were negative. If it's sufficiently strongly negative, this whole quantity can be negative, and that will flip the sign. Instead of a minus sign, a deceleration, if we flip the sign, that's a plus sign, and we get an acceleration. We get some acceleration of the expansion of the universe. So that's like you throw a ball up in the air, and instead of it slowing down under gravity, instead of it decelerating, it's going to accelerate. It's going to shoot off. So it's like an anti-gravity. It's a very strange situation. And so the question is, can we ever get a negative pressure? Does that make physical sense? And so you can get a negative pressure. When you suck liquid through a straw, you are creating a negative pressure. You're drawing the liquid up against gravity. Trees do this all the time. How do the trees get water to their upper leaves? They draw it through the ground, they draw it up the trunks through capillary action, and they get to the top of the tree. Negative pressure does exist. In quantum physics, negative pressure is a very interesting quantity, and it does happen in quantum physics. So it's a very deep deep thought, this negative pressure. Yes.
Here we have density, and pressure.
Yes.
And what about physical dimension? Can we make some?
So remember, our universe is homogeneous and isotropic. So what we're saying is the density and the pressure are the same everywhere in the universe. So there's no, it's not a particular object, but it's a uniform fluid, basically, filling the universe. So there's no dimension except for the dimension of the universe itself. So A is that scale factor of the universe as a whole. How does that expand over time? Okay, so now let's do the experiment. Let's actually go out and make the observations and ask, how is the universe expanding over time? Is it accelerating? And so the way that you do that is you measure those distances. Remember the analogy of the tree rings. We look at distant objects and we measure how does their distance change over time? How does that scale of the universe change over time? So we need a very bright object to be able to see far across the universe. And one excellent object is an exploding star, what's called a type 1a supernovae. This is basically a star that completely explodes and disrupts. It undergoes a thermonuclear explosion in its core as it heats up, and then it just completely explodes, leaving nothing behind. It just gives off this immense flash of light. And so in the 1980s, people learned how to view these at greater and greater distances because of technology development, new types of sensors, detectors, called charge-coupled devices. And so again, you learn the physics of material science, and you couple it to the telescopes in astronomy, and you're able to see fainter and fainter objects. And this is one of the main goals of the Energetic Cosmos Laboratory here, is developing new generations of more and more sensitive detectors in different wavelength bands. And so we can measure these supernovae at greater and greater distances and ask, how did the universe expand? So we're here today at scale factor 1, we just normalize it to 1, and we start looking back in time and ask, okay, the nearby supernovae, how far away are they? We go a little bit further out, how far away are they? And we just keep tracing that curve back as far as we can manage with the observations. And so this was the program in the 1990s by a group led by Saul Perlmutter at Berkeley and by Brian Schmidt at Harvard. And what they found is that the shape of this curve was very, very interesting. So remember, a second derivative of a scale, of a position, is an acceleration. And so if this curve bends over, then its second derivative is negative. It's like you throw a ball up in the air, it goes up, it starts to slow down, it turns around and comes back. That means it's decelerating. It turns over. If that ball started to go up and then started to head off into the sky, something that doesn't usually happen, that's an acceleration. That's an expansion faster and faster. And if we look at this curve, we can see just by eye, it goes up, it's starting to decelerate, it's starting to turn over, but then as we get about here, it starts to curve off in the other direction. So it starts off decelerating, but at some point in the universe's history, it now starts to accelerate. The sign changes. We must have something with this negative pressure. So we give the name of dark energy to this. We could have just called it negative pressure fluid, but that's not as popular in the press, and so people call it dark energy. So the supernova told us there had to be some dark energy. And so the two groups that did this experiment won the Nobel Prize in 2011 for this discovery of this cosmic acceleration. What is incredibly interesting, again, this negative pressure that you need to do this is not something that we've ever found among a material in the laboratory. If we heat up a gas, it's always showing positive pressure. If we look at photons and radiation, whether they're X-rays or radio waves, they always have positive pressure. We never found a material in the laboratory, in the Earth, that had a negative pressure. We knew it was theoretically possible. We never found it. And yet we're finding it out there in the universe. So it's something very different from normal physics. So that's why it was such a great discovery that it implied that it was worth a Nobel Prize. Now what's even more interesting is this period of acceleration, which is happening in the last 6 or 7 billion years. We actually think, theorists think, that way, way back here at the beginning, there was a just a fraction of a second after the Big Bang, that there was another period of cosmic acceleration. That it's happened twice. And Professor Hazumi's talk this afternoon will talk about trying to map this out all the way at a few seconds, a fraction of a second after the Big Bang, and how this would have immense implications for understanding physics, understanding quantum physics in the universe, gravitational waves, and so forth. So I'm going to talk about this cosmic acceleration. Professor Hazumi will talk about how we can explore the cosmic acceleration in the first tiny fraction of a second. So when we take that curve, and by measuring exactly how much deceleration and how much acceleration, remember that tells us about the contents of the universe. It tells us about the pressures and the densities. And so we can then put together basically a diagram of how much of each type of matter and radiation and so forth there is in the universe. And what we find is a very small fraction is the type of stuff that make us up. So less than 0.03% are the elements in the periodic table, the things we're used to. There's hydrogen, helium gas out in the universe that stars form from. There's about 4% of that. So that eventually becomes stars like our sun and planets. But then most of the universe, there's about 25%, which is a very strange material called dark matter, which I won't have a chance to talk about today. And then about 70% is this dark energy, this accelerating substance. So that's the picture today. But again, it changes over time. And what we'd like to map out is the percentage of each of these types of material as we look back in time. So we have this completely new material, which is not in the periodic table. It's not in most of the textbooks. It's a new discovery in the last 20 years. And again, the students in the audience, you're the ones who are going to bring this forward. And 20 years from now, you're going to say, these people knew nothing. There was all this universe that they didn't appreciate. All these new types of physics, new types of materials they didn't know about. And you're going to be the ones who are going to discover it. So it's very exciting to be in this subject. So again, you're going to fill in 95% of the universe. You're going to say, my professors, the people who taught me in classes, they knew 5% of the universe. I'm going to learn about 95% of the universe. Okay. A little bit of philosophy, and then again I'm going to accelerate my talk and get into the research a little bit more. Copernicus taught us what we call the principle of modesty. The Earth, when we look out in the sky, we think, oh, we're the center of everything, the center of the solar system, the center of the universe. And Copernicus and Kepler, people who made astronomical observations with great precision, realized, no, that is not true. The sun is at the center of the solar system. The Earth is just one of the planets. And so we call it the principle of modesty because it said, we're not as special here on Earth as we thought. We're not at the center of the solar system. Maybe though we're still the center of the galaxy. We learned at the beginning of the 20th century, as astronomical observations got better, no, we're actually fairly far out from the center of the galaxy. And our galaxy is not the center of the universe. There really is no center to the universe. Everything is expanding away from everything else. The discovery of dark energy in 1998, so this sort of discovery, said the stuff that's us is also not the typical stuff in the universe. We're not the stuff that the universe is made of. The particles that we create here in the laboratory are not the main matter and energy of the universe. Again, we have to be very modest that there's all these things still to explore. And so now we have these almost philosophical questions that we don't know the answers to. Is our vacuum the vacuum of the universe? When we create a vacuum in the laboratory, what we mean by that is we've cleared out of that volume all of the particles that we know about. But we don't know about dark matter. We don't know about dark energy. Is there a different vacuum? So the vacuum is a quantum physics concept. So do we understand quantum physics well enough to know what a real vacuum is? And so that's a very deep question. The other possibility is we don't understand gravity. Just as Einstein extended Newton's theory of gravity, one of you maybe will extend Einstein's theory of gravity. Because this acceleration, this idea of throwing a ball up in the air, and instead of it falling back to the ground, it shoots off in the sky, acts opposite to gravity. And the universe seems to be working that way. So maybe there's something about gravity that we need to extend from Einstein. So these are very deep science questions. So as I say, I'm going to accelerate a bit more and basically say the questions we want. We want to get some idea of what it's made of. And so we define what's called an equation of state, which is the ratio of the pressure to the density. You can think of it as the springiness of space. Remember, we said that gravity and acceleration is the same as the curvature of space-time. And so we want to know if you push on space-time, we push on the curvature, how springy is it? How much does it go down? How much does it restore? So just like you sit on a bed and the bed goes down, you put a certain mass on the bed goes down. Depending on the springs in the bed, depends how much it goes down under the gravity of your weight. We want to find that same thing for the universe, how springy space-time itself is. And that will teach us about space-time, about this dark energy. And we want to know, do we need to extend general relativity or not? So to talk about quantum physics, you talk about field theory. So some of you may be experts in field theory, and others of you might be a little nervous, a little scared of field theory and say, oh, these are very complicated mathematics. I really don't want to learn about the quantum nature of the vacuum, all that field theory. But in fact, I want to convince you, you already know field theory, because all field theory is a field. And so as you look out, maybe not today because everything is covered with snow, you look out at the spring, you see the grass across the steppe. And you say, if I wanted to, I'm not sure why I would want to, I can measure the height of grass at every point in the steppe. And so at each point in my space, I measure a length. How tall is the grass here? How tall is the grass here? How tall is the grass here? That's all that field theory is. I'm measuring one number at each point in space. That's called scalar field theory. You get one number at each point in space. See? You know field theory. You can elaborate that, and you can say, let me do vector field theory. In that case, you have a direction at each point in space. And so you look at the grass on the steppe, and maybe the wind has blown the grass over, so it points in a certain direction. In another place, the wind has curved around and blown the grass in another direction. Or maybe a horse has trampled the grass in some directions. So at each point, you have the length of the grass, and you have the direction that the grass is trampled down in. That's vector field theory. See, field theory is not as difficult as you may have thought. So field theory teaches us about the quantum nature of the space-time. Gravity, again, I'm going to leave for so this is the field theory. This relates the field, this parameter phi, to the energy density and the pressure, which tells us how fast the universe is expanding. Here are some equations. You can go through those at leisure. In the end of the slides, I actually have some exercises. So if you want to practice your field theory, you can do the little exercises. So especially if there are students interested in researching this, then try the little exercises at the end. Here are some limits. Here are the equations. Suppose you wanted to actually do cosmology. You wanted to calculate how fast the universe expands in a particular field theory. These are all the equations that you need. I have a principle in my talks that if you see lots of equations, then some people react differently. Some people, they get very nervous. Oh, look at all these equations. I don't want to deal with it. Some people fall asleep. So whenever there's a lot of equations, I say, put a calming picture up as well. And so here are the equations, but there's a calming picture in the background. So this is a picture of Berkeley. So this is from basically my office in Berkeley. This is the city of Berkeley. Here's the campus. Here's our bell tower. And this is looking across San Francisco Bay to San Francisco. So you can calm yourself down while you study the equations. Okay, we should do a picture with Astana as well. Okay, so again, you'll have these slides on the web. If you want to go through the equations, then you can go ahead and do that. We talked about the growth of the universe as a whole, the expansion of the universe as a whole. In addition, you also have the growth of the structures within the universe, right? We talked about a homogeneous and isotropic universe. It's the same in all volumes. We know that's not true. if I am in this volume, then I can walk around. If I'm in this volume, there's a table in my way. This volume is not the same as this volume. It's only when you do the very largest scales in the universe that you can say, on average, that volume is the same as that volume. But if we want to talk about things like desks, like where planets are, where galaxies are, then we need to include the fact that things are not perfectly homogeneous. And then that changes over time. We know that the planets formed out of clouds of dust that coalesced under gravity, that formed planets, formed stars. So matter grew. And this is the equation for the growth as a function of time. So these double primes are basically as derivatives of time. And so it depends on the expansion. So h gives us the expansion rate that we talked about with the supernovae. So this is a very simple equation. This equation will change if your theory of gravity is not general relativity. It's growing under gravity. If you have the wrong theory of gravity, that will give you a different growth. And so by measuring the growth of large-scale structures in the universe, we can test the theory of gravity. So we have these two very important things. How does the universe as a whole expand? And how do the structures, the large-scale galaxies, clusters of galaxies, grow over time within that universe? These are our two main cosmology ingredients. So this says that same thing in words, basically, talks about ways of testing it and so forth. So now let me get to actually how do we start to test this with experiments? And what are the advances in technology and in thought that are going forward? So again, I'm going to go back a few centuries first. Some of you may have read this book. It's a very good book. So in the 1600s, as people started exploring the surface of the Earth, they would sail in ships and they would go off until they found some new land. And they would want to know, well, where are they now? Where is this new land? They would want to create maps of the Earth. And so as they sailed along, they could observe the stars and they could say, okay, if that star is always the same height above the horizon, then I'm on a line of what they called constant latitude. Okay, so the latitude of Astana is 52 degrees north, something like that. Okay, and so you can go around the Earth at 52 degrees latitude and you could know where you are. But if you're sailing across the ocean, you don't have any marks. It's just, the ocean. You don't see any land, any mountains. You also need to know where along that circle of latitude you are. You need to know where you are east-west, and that's called longitude. And people did not know how to measure longitude. It was very difficult to measure it just from the stars. And so the Royal Society offered a prize. Whoever could measure longitude accurately on a moving ship would get a prize of money, be rewarded. And so this was called the greatest scientific problem of the time. How to map out in a second dimension. You can map out north-south the Earth. How do you map it out east-west? How do you map out that extra dimension? And what he did is he developed, and this is a lone genius. So this is like Professor Gabanitz was asking, how many people does it take to do a scientific discovery? Back then, it took one person. Okay? Sometimes today, it takes thousands of people. So the lone genius who solved the problem. And what he did is he built a very stable clock. So he built a new technology that had good stability, good resolution. So those are going to be very important. You'll hear Professor Hazumi talk about this for when he builds satellites, when he builds detectors. And he was able to expand from this one dimension of mapping to two dimensions of mapping. And it worked very successfully. So the problem that we have now in the universe is we can look out in the universe and we can map in two dimensions very well. We can figure out where it is, basically, where a star or a galaxy is in latitude and longitude on the sky. But how do we measure the distance away that it is? How do we map in that third dimension? And the technologies that we've had until recently have been very slow. It takes a lot of time on the telescope to measure that third dimension of distance. And so I'm going to generalize this from the 1600s to today. And that third dimension is called redshift because, again, it shifts the frequency of light. And what we see is it's no longer a lone genius, but now it's collaborations of scientists, hundreds of scientists who come together to figure out how to do this. And it's not a simple instrument like a clock that can just sit on the desk, but this shows a picture, I have a better picture later, of basically thousands and thousands of optical fibers that are adjusted by robotics to point at the galaxies and to measure their distances. There's so many thousands of them that if you tried to plug the fiber in to point to the galaxy, it would take you a very long time to do all of this. And so we need to develop basically robotics to be able to do this very quickly. Once we can measure the three-dimensional distribution, we learn a lot about the universe. Again, that growth of structure in the universe. We can learn what makes up the universe, how much matter, how much radiation there is. We can learn about particles called neutrinos that Professor Azumi may mention. We can test gravity and so forth. So the current surveys, so this shows basically this third dimension of mapping. I don't know, is it possible to turn the lights down near the fronts so you can see this a little better? So the third dimension of mapping, and this shows a certain volume as we look out in the universe. What we are looking for the next generation is we do 25 times better than we do now. We map much, much more of the universe than we do now. I won't get into this, but I'll make the point that as we map the universe with more precision, then we also need to be clever in how to interpret the data. And so we're getting many terabytes of data from our observations, and we have to figure out, well, what are the important pieces? So we need to be very good at computing that data. We need to be very good at the statistical tools to learn the data. And the theoretical formula to predict, so this is basically a power spectrum, we see that gives us the green line as the prediction of this formula. And when we do our computer simulations, we get the red line. We see that very quickly this simple formula breaks down. We want to be able to measure this to basically 1%, very, very small error bars. And so we see that the theory needs to advance. We need to have some clever people figure out how to structure really grow in the universe to predict it theoretically to compare to the observations. And so it takes a blend of theory, statistics, and computational expertise. And that's one of the things that we want to do here at the Energetic Cosmos Laboratory, is develop these theoretical and computational tools. Here's an example of an experiment called the Dark Energy Spectroscopic Instrument. And what it does is it has collections of these spectrographs measuring the spectra of the light from these distant galaxies. And it has about 5,000 of these optical fibers. And so you need to characterize the optical fibers very well. Again, there's an excellent material science and robotics departments here. And you need to be able to move those fibers around very quickly on the sky to point to the new directions of the galaxies. And so this is another area of technology that we can collaborate with the departments here at Nazarbayev University on how do you make these very tiny motors, basically, that can be robotically moved around on the sky. Okay, there's a movie which I've also given the link here. I'm not going to play I'll play a little bit of the movie if I can figure out how to do that. If I can find where the cursor is. Okay. Okay. So the movie's about 2.5 minutes long. You can read the whole thing. So this is called the Sloan Digital Sky Survey. It's mapping about 500,000 galaxies. The next generation will map 30 million galaxies. And so what you're going to see is you're going to see the actual data. So here you're flying through the universe. Each one of these is an actual galaxy that was measured by the Sky Survey in the correct positions. They're much larger than you would actually see in a photographic plate. But here you can see, as we go further and further back in time, you see the types of galaxies change. And they start to become these little faint red galaxies because they're very early galaxies. They're still forming. So you have these sort of very early red galaxies. As you go further and further back, then you start to also get to quasars. These are black holes giving off giving off immense jets of energy. And so soon you'll get to the quasars, which are going to be these little sort of blue dots as we get further and further away. So this pattern is simply because that's where the telescope was looking. Okay, there's also the same galaxies all everywhere else, but the telescope was focusing. You can see it was focusing in these narrow slices. And you can see this sort of spongy distribution of galaxies, but on very large scales, it's homogeneous, that you have the same number of galaxies. So here are these quasars. We've now gone about 10 million years back in time, and eventually we get to the cosmic microwave background that Professor Azumi will talk about, which is 13.5 billion years back in time. Okay? So he will talk about that this afternoon.
The correct position of stars, yes?
Uh-huh.
So, do you consider a gravitational effect of some? So we can't say that the light is a straight line because we have a gravitational effect.
That's right. So you're saying the light is being bent by the gravity of the structure.
So we can't say that the correct position.
That's right. This is called gravitational lensing. So it's the same way light gets lensed as it passes through the glasses in my eye. And this is a very active area of research. And people are doing surveys to measure this. It's a very, very hot topic. So if you're interested in that, that's a very good topic to do research on. So what we see in this is the galaxies that we've mapped is a very small part of this whole volume. And in the next generation, we're going to map a larger volume, but we're still not going to be able to map the whole universe. And so there's a lot of work still to do in observing the universe. And then Professor Azumi will talk about, as we look back to this surface, this relic radiation, the cosmic microwave background, this green and red and blue, what we can learn from that as well. Okay, so again, I'm going to accelerate along. We talked about how light brings messages from the past. So now I'm going to talk about the light, that cosmic microwave background that Professor Azumi will go into detail of. I'll give you a little bit of a taste of it this morning. What about that most ancient light? So this is what that glow of radiation from the Big Bang looks like. It looks like the same in all parts of the sky. Okay, that's what we talked about, isotropy. What is this strange oval? Well, you're used to, no? Missed. I think I got rid of a slide in between. This is a projection. So the same way that when you have a map of the surface of the Earth, unless you have a globe, when you try to put it on a two-dimensional surface like a screen, you have to spread it out. Okay? And so this is just a projection onto the two-dimensional surface. And that's why it looks like this ellipse. This part is really the same as that part. It wraps around. Why does it look why does it look the way it does? Why is there a glow at all? And again, Einstein came up with this incredible simple way of explaining the physics. That all you really need to know is E equals mc squared. The early universe was very, very hot, very, very dense. And so E equals mc squared says if it's very hot, that means there's a lot of energy. So a lot of particles can be created. The energy can be converted into mass. E goes over to mc squared. So now you have all these particles running around in the early universe. Once the particles are running around, occasionally they collide, they interact with each other. So that's all particle physics. Sometimes a particle and an antiparticle can annihilate, and then they go back to being energy. So mc squared, mass, gets converted back to energy. In the early universe, this is happening all the time. When it happens in both directions, you get what's called thermal equilibrium. And so you just get this glow of what's called black body radiation, a very particular energy spectrum that the physicist Max Planck predicted. You can measure the temperature of this black body spectrum by basically where it peaks. Does it peak in the blue? Does it peak in the red, in the infrared, in the millimeter, the radio waves? In the same way that the color of the flame tells you how hot it is. The blue is the hottest part, the yellow is medium heat, and the red is less hot. You can measure the temperature from the spectrum, from the color, basically. So again, that's what it looks like. Okay, here's where I show the projection. So this is what the Earth, the globe of the Earth looks like. And all we've done is we've projected it onto this two-dimensional surface, into this ellipse. And that's exactly what this is for the cosmic microwave background sky. Again, why does it look so exciting? Because it was in thermal equilibrium, the same temperature everywhere. And that tells us something important about the early universe, that it was this hot, dense state. However, is it perfectly uniform? And so that was a very exciting question for the experimenters to go out and try to do. And in 1992, a satellite called COBE discovered variations of 1 part in 10 to the 5th, 0.001%. And so if we take away the uniform part, then this is what's left over, these small variations, 3 degrees plus 10 to the minus 5, 3 degrees minus 10 to the minus 5. Slightly hotter, slightly colder spots. So this was done in 1992, and again, it was such an important measurement that it won the Nobel Prize. So George Smoot, who is the founder of the Energetic Cosmos Laboratory, won the Nobel Prize in 2006 for this discovery, along with John Mather, who was the leader of this COBE satellite for measuring the black body spectrum, this thermal equilibrium spectrum of it. So again, these hot and cold spots mean more dense and less dense spots, the formation of structure, what we call the seeds of structure. And Professor Azumi will talk more about this. The way we measure how much variations are through what we call the power spectrum. Basically, how strong is the amplitude up and down in this spot versus how strong the amplitude up and down is in another spot. And in particular, two spots close together may be correlated. If this one's hot and you're very close to it, you might expect that one to be hot, whereas a spot far away could be hot, could be cold, that there isn't this correlation, that the variation here should not influence what the variation far away from it is. And that's exactly what this power spectrum is. So Professor Azumi will be showing plots of the power spectrum. In your mind, just think about it. It tells you about the correlation of structure across different scales. So across different angles on the sky. We often like to go to what's called multiple space. That's just 1 over the angle. So a large angle is a small multiple. It's just something that physicists do. We could always do it in terms of angle, but people seem to prefer doing it in terms of this inverse angle, this multiple. We can also do it in terms of what's called the wave number. So this is the Fourier modes. So that's another very good way when you do time series, for example, of an event, of how something varies over time, you will often talk about things in terms of the Fourier transform. Remember we said that the temperature variations, the hot and cold spots, are directly related to the density variations, where the universe is a little bit more dense, a little bit less dense, at that 10 to the minus 5 level. So we also talk about the density power spectrum. So I've written the changes in density, the variations in density, and that's written with the symbol P as a function in this Fourier space. And again, the universe is so simple that we think that a very good approximation of this power spectrum is simply a power law, that it depends on the scale to some power law index. Professor Azumi will talk about how the measurement of this power law index tells us a lot of fundamental physics, the quantum physics of the very early universe. So this is what the power spectrum looks like in the microwave background, and this is the corresponding power spectrum in the matter density. And so the two are very closely related to each other, that where you have these peaks and dips, that correlates with the peaks and dips in the matter power spectrum. That the two are basically images of each other. And so we can measure things in the microwave background, or we can measure things in the galaxy distribution, and we expect them to be related. So we can learn something from each of those. Okay? So the experiments to map the galaxies and the experiments to map the microwave background are both very important in learning about the universe at different epochs, at different stages in history. So where did these hot and cold spots come from? Why isn't, if we said that things were in thermal equilibrium, why isn't everything just uniform? And so this is a very deep question we don't know the answer to, but the leading theory is what's called inflation. This is a quantum physics process that creates these tiny variations. Remember the scalar field? We talked about the field of grass. Why aren't all grass heights the same? Because there's little variations from one point in space to another. And inflation, we think, creates these variations. Professor Azumi this afternoon will talk about inflation and the deep quantum physics relations. Again, inflation is that very early period of cosmic acceleration. I talked about the late period of acceleration. The universe is expanding. You have the dark energy. He's going to talk about the one that happened 14 billion years ago, called this cosmic acceleration called inflation. So this was the picture that I showed you from the COBE satellite. Technology, instrumentation has gotten much, much better. They launched another satellite called WMAP, which gave us a much finer picture, higher resolution picture. And then most recently, there was a satellite called Planck, which gave us an even finer picture. Professor Azumi is the leader of a proposed satellite called LightBird from the Japan Space Agency, and he will discuss today and tomorrow what sort of a picture LightBird can give us. And it turns out it tells us not only about the hot and the cold spots, but it teaches us about something called polarization, a completely different window on the early universe. So here's our picture of the microwave background as we have it now. And this is a baby picture of the universe, okay? Slightly after the Big Bang, a few 100,000 years after the Big Bang. The next step that Professor Azumi will talk about is then to look, instead of 100,000 years after the Big Bang, to look a small fraction of a second after the Big Bang by using this polarization information. So at 2 o'clock this afternoon, Professor Azumi will give his lecture in this room. Again, the slides will be posted on the web, and following this slide are some slides with a few exercises in case you feel challenged to do some calculations, and also some references for further reading if you are interested in some of these topics. So I'll stop here, and I hope we can have some good questions and some good discussion now. Thank you. So do we have questions? Yes.
Yeah, can you go to the page 44 or 10, please?
Oh, is it 44? No, then 43, I guess. Yes, that one. The other side, there is other side of this picture, right? On the left side.
So this is we map the history with the tree rings on Earth. So we can learn again about the history of the Earth, the climate on the Earth. Even though we didn't live 1,000 years ago, we can tell what the climate was like 1,000 years ago by looking at how quickly the tree grew in this year versus this year. So we can recreate the climate, and then we can know, is the climate today the same as it was 1,000 years ago? Is it growing warmer, for example? These sort of things. So we learn about the past history, and that's an analogy to how we can learn about the history of the universe.
All right, I see. But the expansion of the universe, it's isometric, right?
Yes.
Yeah. So there is another side.
Right. I've cut in half the full picture of each of these.
All right. Then how far, the farthest distance that we can look? So there is a Big Bang at the center, and we are, for example, going on the right side, and there is some kind of symmetrical temperature, same temperature expansion going on the left side.
Yes.
But we don't know anything about it yet, right?
So it's important to remember that in this picture, the distance from the center, it's not really a distance in space, it's a distance in time. So this is time 0, time 100,000 years, time million years, time billion years, and so forth. So yes, it's symmetric about this, but it's not that we're looking in that half of the sky, that half of the sky. We want to look at the whole sky, and this is really showing the evolution in time. So think of this as the time dimension, not the space dimension.
This picture is symmetric one.
Yes, that's right.
This is very easy.
I just cut it in half so that I could show half the tree ring and half of the universe.
When I was schoolboy, sixth class.
Yes.
Our teacher taught us about this. I'm repeating once again. When I was schoolboy at sixth class,
Yes.
Our teacher explained us these rings of trees.
I think it's a very good analogy how we can learn about the past.
Old problem.
Yes.
This is school problem.
Ah, good. Some more questions?
Maybe Is it possible? Small,
Dear Eric, you explain us about the cosmology and so on. You talk about the vision of cosmology of Nazarbayev universe only. But tomorrow I want to say a few words. This will be I'm asking you, may I make a small report, maybe 10 minutes, 15 minutes, about the history of development, general relativity and gravitation and cosmology in Kazakhstan in total. What do you like? Is it possible?
This is a very good point that I was talking about Energetic Cosmos Lab because it's new, so I want to make sure everyone knows about it.
Yes.
But yes, there are research groups throughout this university, from many other universities. We're very glad that
Because the
faculty from other
patriarch of
universities.
physics, academician Fogg, academician Fogg.
Yes. Yes, very famous.
When you have written that gravitation equals curvature and acceleration, this is Fogg's namely idea, because because Einstein put forward the principle of equivalence, m inertial equals to m gravity, and no more. But next step in logical understanding the general and in Almaty, worked two students of work, Petrova and academician Abdildian, and I think it will be interesting and for you also about this historical remarks.
I agree. I was talking about how cosmology as we observe it is so simple, but we know general relativity is not so simple. And academician Falk and his students were instrumental in categorizing all the different types of space-times you could get in general relativity, all of the interesting properties of general relativity. I was talking about how simple it is, and they were going very deep and saying, look at this rich structure, all the possibilities. So yes, that's very important. Also, I want to mention international collaborations. These surveys, again, it's no longer just one person in their laboratory making these big surveys of the microwave background of galaxies. It's international connections. And so we want to encourage the connections with Kazakhstan, we have our guest from Japan. Professor Smoot is currently in Hong Kong talking to the universities there. We have people from Energetic Cosmos Laboratory going to the laboratories in Paris in a few months to learn about what's going on there. The global nature of science is very important. You want the best minds from everywhere to come together. And so I think it's a very encouraging sign to see people from several universities within Kazakhstan coming together and talking about this subject. Yes.
Can it, just a second? Because we have coming here.
So initially we have a point, when before Big Bang, and we have nothing, yes? So we have a burst, immediately after Big Bang. And Einstein says that the speed of light is the faster speed in the universe. So how we can see the light from Big Bang if the universe is...
So these are very, very deep questions, and we don't know the answers. So as we go to, I said this was time zero. We don't know. Can there be a time before time zero? These are questions, we don't even know how to phrase them within the equations of science, within the physics. So we can't even ask the question in the right way. The main issue is that we know that quantum physics tells us about when things are very, very small, when they're subatomic size. Remember, the universe is expanding, and so as we look back in time, the horizon of the universe was smaller and smaller and smaller. Eventually, the gravitational aspects become very large because all of that density is in a smaller and smaller place. And basically, the universe becomes like a black hole. And the quantum aspects, because they're so small, become important. And we don't know how to merge the gravity and the quantum aspects. We don't have a theory of quantum gravity. So we don't know how to ask the question that you want to ask. What happened at time zero? What happened before time zero? Again, the students in this room, maybe they will come up with a theory of quantum gravity. Maybe they will extend Einstein to merge with quantum physics. But this is a topic that people are thinking about very hard, but we haven't figured out the right question to ask. But it's a very, very interesting problem.
Your words. This question, of course, this question is very important, but Linde, Professor Linde from Moscow University, initially, you know this, he considered the following. When we talk about the stage of inflation, in this stage, there is no transport of energy. That is why the speed may be more larger than the speed of light. But this is answer for your question. But at more late of the universe, we talk about the process of energy transforming, transferring, and that is why in this case we talk about the processes that elapse with the speed no larger, of course, than light. But of course, this is in the framework of general relativity. But Professor Linde talk about of course, this is not new conception, but it is well known. This is multi-universe conception, isn't it? Yes, when we consider the process of our universe burning and our universe expanding with respect to other space-time form, other bubbles of the space-time form. And you must read the works of Linde.
That's right. And the inflation that Professor Azumi will talk about, the experimental probes of inflation are really our only tool to try to address these questions. We don't know if they can. This idea of inflation that branches out into multiple universes. There are some ideas for signatures that could appear in the cosmic microwave background. And people are looking for such signatures. But again, maybe we're not asking the right questions. We don't know yet. It's a topic of very active thought. Yes.
But some answers on this question we have.
Okay, good.
They are not correct. Nevertheless,
well, what wasn't it Lev Landau who said a cosmologist is never in doubt, right? He's always has an answer, but it may not be the right answer, right? It was we have our theory at the moment, and then the next generation says, you didn't ask quite the right question. Instead, you want to talk about this way. Yes.
Back to the philosophy of if you can't explain something simply, you didn't understand it well, right? So can you describe the universe that this question kind of disturbed me most?
The universe as a whole.
Yeah, can you describe it?
So as long as you're talking about the property of the universe as a whole, obviously if I were to describe the universe, I would have to say, this person is sitting here, that person is sitting there. There's just, we can't describe it on the microscopic level, where that atom is. We have to describe it in a statistical sense. So in a statistical sense, the universe is to a very good approximation this homogeneous and isotropic. Roughly the same in different volumes, same in different directions. It is expanding. That expansion history started from a hot, dense state, a Big Bang. It expanded, it cooled, it formed structure within it. I've gone way over one sentence, so you can see that I'm not explaining it as simply as you would like, as all of us would like. But the universe is a big, complicated place. Maybe, you will one day understand the universe so well that you can explain it in one sentence. So these are the general statistical properties. An early hot, dense state, we call the Big Bang. It's now cooled, structure is formed, and it looks roughly the same in different volumes in different directions. But there's so much rich physics within how do stars form, how do stars die and explode, how do black holes form. I don't see that anyone will ever describe in one sentence all of that. which is a good thing. It means that there's work for every person in this room, every person at all the universities to try to understand the universe. Yes.
So I want to talk about the light. If the photons haven't mass, yes. So how photons to make the curve when he reach through the gravity? So can we explain by Einstein? You said that the acceleration force and the space curvature is the same.
Exactly.
So can we explain with this theory the photons?
Exactly. You have the kernel, the center of the question. We can either say a photon has no mass, but it does have momentum. And if a force acts on it, that changes the momentum, right? That is what a force is, a change in momentum with time. And therefore, as momentum changes, it curves. So that's the way viewing it in terms of an acceleration. If we view it in terms of a curvature of space-time, then what we say is the photon is just traveling on the shortest path. It's traveling on a straight line in a curved space. You don't need to say anything about forces. The photon doesn't need to know anything. It's just taking that shortest path, what's called the geodesic. And that's one of the very attractors of geometric approach. The photon curves only because we're looking at it in sort of outside this curved picture. If we viewed it in the curved picture, the photon is just traveling essentially straight on the shortest path, on the geodesic. And the pictures, Einstein taught us those two pictures are exactly equivalent. Any calculation you do one way will give exactly the same answer as the calculation you do the other way.
So, the Lagrange equations considers the minimal action of
yes.
So can we say that it's the same thing like Lagrange equation? So like a minimal action.
Exactly. So the slide that I went over very quickly with general relativity, the way you get the equations of general relativity, which give you the Friedmann equations, are you have a Lagrangian and you're doing the principle of least action on that Lagrangian, on that action. So yes, you can use all the Lagrangian mechanics that you do in your classical mechanics. You can use that in general relativity as well.
By the way, photon possesses mass, but moving mass, isn't it? Moving mass.
It's a word. In the scientific concepts, we would say it's a massless particle. It goes on null geodesics. Gravity acts on it. Yes.
So my question is about modified gravities. What do you think about such theories? Because it is good candidate for dark energy.
It is. So several of the slides I went through very quickly talked about how we would like to test modifications of gravity. And there's some very, very clever ideas out there of how to do this. So far, none of them give predictions that are better than general relativity. Every observational test that we do in the universe, in the laboratory, general relativity can explain. So we haven't yet found a deviation. And so general relativity is such a simple theory when you view it on the theoretical point of view that we have no motivation to abandon it. But again, the other theories are just so interesting that a lot of people continue to work on them. And it's good to compare general relativity to modified gravity and eventually look for some observation that gives you a definitive test. So it's a very interesting area.
So I am asking because for me I can't understand how the nature can choose one of modified gravity from continuum of such theories. So this is what is interesting for me. I can't understand this. So
that's right.
In this case, I think that maybe what you said that Einstein gravity is much simpler, the simplest gravity theory, and so maybe this is the reason why Einstein gravity is correct theory.
That's exactly right. In the 20th century, physics was enormously successful applying symmetry principles to figure out what the right theory is. General relativity has these beautiful symmetry principles. Particle physics has these beautiful symmetry principles. If your modified gravity theory also has beautiful symmetry principles, does that mean that it's right? We don't know that beauty is truth, right? What we think of as beauty is that what the universe thinks of as truth. But it's been so successful, this application of symmetry principles of group theory, that it's very tempting to try to continue that trend. We just don't know if the universe decided to choose that theory rather than general relativity or not. Good. So maybe, let's see, if Aliyah, oh, we have another question? Okay.
Thank you for your lecture. And my question very simple. Can you give us some idea, or maybe you know the model, special action of dark matter? Because dark matter, you know about this, act in cluster galaxies.
Yes.
And no in ordinary our surrounding. Please, some comments on this.
Dark matter, so I talked about dark energy. I showed on the one slide in that energy budget of the universe that 25% of the universe is dark matter. That's a fascinating topic I haven't had the chance to talk about. Dark matter is very interesting because we can look for it not only out in the universe by looking at the structure and the growth of galaxies, by looking for annihilations, for high energy gamma rays coming from dark matter annihilating, but we can also look for it in the laboratories and in deep underground mines here on Earth. And so it's, and in particle accelerators as well. And so you have these multiple ways of looking into the dark matter problem. And because we have so many different ways and so many different clever ideas that the research groups have, my prediction is that we're going to learn more about dark matter in the next few years than we will about dark energy. But if Professor Hazumi's plans for the satellite go forward, then we may learn a lot more about dark energy. But dark matter is again, it's this new area of physics. There are many ideas for how to detect it, and I hope that we will detect it soon, and that would be wonderful. There are many ideas. There are these weakly interacting massive particles. There are axion particle ideas.
Yes, I know.
We need some experimental evidence to show us the right direction.
Excuse me, but all idea or models sent about action of dark matter,
yes.
And they cannot give answer why they act more effective in galaxy clusters, but in ordinary galaxy, no.
So again, today I concentrated on dark energy. Some other research conference, maybe we can get into dark matter more.
My report will be on.
That's right. We will hear a talk on a model of dark matter this afternoon. That's true. Yes, today, this afternoon, after lunch. Yes.
Can you say about the here there was in slides the graph some curvature was. So can you tell about it again?
The supernova mapping out the history, is that curve? Or which?
Yeah, I think so. I'm not sure.
That was early.
Oh,
this one?
Yes.
Okay, so what is your question about it?
So it's so this graph shows us all the light. I mean,
each of these points is measurements.
We can see the galaxy through the time.
Yes.
So you said that we have some curvature. So he goes up. It's because of dark matter or dark energy.
We give the name. What we measure is that the curve turns up, that means the second derivative is positive, and we just give the name dark energy. It's just a name. It doesn't tell us what it is.
So
We have to do better measurements to understand what exactly we mean by that name.
so maybe this means that the light have changed the speed when he travels.
So exactly. So that was one idea, that maybe you are somehow changing the properties of light, and people have tested that and found that no, the properties of light are the same. You're not losing energy from the light, for example. So that was an idea. People tested, and they said no, that is not explaining all of the data. That it must be the expansion of the space itself that is accelerating. Yeah. So it's a good idea, and a good theory can always be shown not to be right. And so people did the observations and said, a good theory is one that can be shown to be wrong. So it's something that can be tested.
Okay.
So,
Any
Aliyah,
questions?
maybe you can tell us the plan for the rest of the day. So,
We have like plans. Now we have a free time. If everything is fine, the next talk will be Professor Hazumi at 2 p.m. in this room, and everybody welcome again. We're glad. And then we have coffee break also at 4:30. We have a talk with Professor Leonid Chechen from Fysenkov Astrophysical Institute also at about more about 20 minutes. Also, then we have talk of Professor Jonas Aliyev from Kazakh National University from Almaty, and everybody welcome again to this. It will be participated. This will be plan of today. So if there is some questions and comments and suggestions right now, if not, we can be free and have a lunch. Then we'll see it everybody at 2 p.m.
very good. Thank you very much.
Thank you so much. I just want to say thank you for who participated in this seminar. There are some students from Eurasia National University, and we have these two active students from Nazarbayev University, School of Science and Technology and Physics Department also. Also, we have the participant from school, Nazarbayev Intellectual School. She is one of them. So thank you. I'll believe that we can see you today at 2 p.m. Yes, everyone welcome. So, see you at 2 p.m. We can say that the lecture is finished now.
Geometry, please.
Nine. So we have actually very interesting audience. As of half an hour ago, I am teaching classical mechanics, the second year students of physics, and Anwar's here. So instead of doing classical mechanics, I sent them an email. I said, come and hear some modern classical mechanics. So indeed, Professor Masai Hazumi has plenty and plenty of addresses in multiple places. It's going to tell us some great stories about cosmic inflation with measurements in cosmic microwave background polarization. In the old days, polarization was not included. Now you're going to include the polarization in the measurements. And don't forget that you have second year students that they are taking classical mechanics at this point. So you have to give them some insight.
Okay.
Thank you so much, sir.
I'll try. So hello everyone. Thanks for having me. I really appreciate this invitation. In particular, Eric Linder. I should say Professor Linder, but I'm a casual physicist. I wear actually a tie once a year or so, but since I don't know the culture here, I just have this. But please allow me to call Eric. So I really appreciate this invitation, which came originally from Eric. And also I really want to thank Aliyah, who really helped me a lot. Come here, I sent many questions, and so I think this visit is impossible without these helps, and then also from other people, I believe. So I'm really excited to be here. This is my first visit to Kazakhstan. So today I'm going to tell us about tests of cosmic inflation with measurements of cosmic microwave background polarization. When I chose this title, I kind of didn't know what kind of audience I should expect. So you already see lots of sort of jargons, technical terms, but I hope to define them in my talk so that you can at least get some idea on what I'm talking about. And then here, this is not a real picture. Oh, actually, this telescope is a real one, but I embedded this cosmic microwave background polarization sky. You cannot see this from with your naked eyes, but with special telescopes, you are really able to see this sort of special microwave background universe. And then that is very important for us to understand the secrets of our universe. So by the end of my talk, I'm going to touch on two projects that I'm working on. One is the ground-based telescope project named Polar Bear, which I'm working. So Eric is also actually a collaborator of this Polar Bear project. This was originally started by my colleagues at the University of California at Berkeley, and we also joined this project and then enjoying this CMB cosmic microwave background observations. I often say CMB, which means a cosmic microwave background, just an acronym. And then the Lightbird is a satellite project I'm now pushing. We hope to launch this in 2020s, in the mid-2020s, for the ultimate measurements of cosmic microwave background polarization. So I belong to this High Energy Accelerator Research Organization, KEK, in Japan. You might not know anything about this institution. There are several large accelerator laboratories in the world. One famous one in Europe is CERN. You might heard about this discovery of Higgs boson recently that was done at CERN. And there's another big accelerator research laboratory in US named Fermilab. And KK is another large accelerator research organization in Japan, and which is doing some flagship accelerator experiments, international projects. I also belong to the Kavli Institute for Mathematics and Physics of the Universe, University of Tokyo. Since I started this CMB polarization measurements, I got this joint appointment there, and then so 80% of salary now comes from KK, 20% from Kavli IPMU. This Institute of Mathematics, Physics, and the Universe, that's called IPMU. Also related to the Graduate School for Advanced Studies, where I'm getting some graduate students. And recently, for this Lightbird project, I'm a sort of a guest professor at the Institute of Space and Astronautical Science, JAXA. JAXA is a Japanese space agency. It's kind of NASA in Japan.
So, Professor, let me ask you a practical question.
Sure.
I'm chair of a department, and I'm always getting confused from where my faculty are getting paid. So you're getting paid from two sources, but
Yes.
you're working pro bono for free for two other organizations. Am I right?
Yeah, these two. Yeah, this is Sokendai. The graduate school is tightly connected KK. So it's a sort of activity inside KK. So I have no problem. This JAXA, this is more sort of casual guest, kind of guest researcher. So again, I see no problem. You need to be a little bit careful between this KK and Kavli IPMU, but we had a sort of agreement, sort of a joint appointment agreement. And actually, since Japanese government recently is pushing toward that direction, so this is a new trend in Japan. Until 5 years ago, it was pretty tough this because I mean both KK and the University of Tokyo are national institutions, so you are supposed to belong to just one of them. Until 5 years ago or so, but now it's changing, so that's why. Okay. So before starting my talk, before talking about the cosmic microwave background, let me continue on my background. I mean, my research history. So at KK, I worked on the so-called B Factory project for like 15 years, since 94 till 2008 or so. This B Factory project was, sorry, it's hard to read, but was about the electroweak interactions of elementary particles, which led to the discovery of CP violation in B decays. I'm not going to go into the detail today, but the happy consequence of this project was the Nobel Prize awarded to Professors Kobayashi and Masukawa. And this, until a few years ago, if you visit the Nobel Prize physics page, you could see this instrument which I built. I mean, lots of people joined this project, but I was involved in this. Unfortunately, now it's changed, so I don't know. We cannot see this anymore on the Nobel Prize physics webpage. But this is the equipment instrument for detecting particle interactions. So I was working on that, and then this is a picture with Professor Kobayashi and me just 2 days after his the announcement of his Nobel Prize. But then in 2005, actually, I made my cosmic survey. The idea was that this is about 10 years ago, but at that time, particle physicists already knew that so-called cosmic connection, the interplay between the cosmology and particle physics, is getting more and more important. So, whereas KK at that time didn't really touch on any cosmology, at least on the experimental side. So I asked myself, what if we bring our technology into experimental cosmology? What would be the best choice? And then this is a bit, to my surprise, I ended up choosing CMB. Because actually, science is gorgeous, and then the technology-wise, we had, I really believe that I convinced myself that the technology-wise, we really have a good match. I mean, the accelerator-based research technology can be brought into experimental cosmology. That's how I started my project. And I don't know why this is missing. Maybe I should, sorry. Yeah, let me check. Yeah, okay. So then I formally established this KK CMB group in 2007. I was lucky enough that the management at that time was sort of enterprising, allowed me to try something new. Then we started some international collaboration. First, the project called Quiet, and the next project called Polar Bear, which we're continuing to now. These are telescopes for measuring cosmic microwave background, or CMB, in Atacama, Chile. This location is regarded as one of the best places in the world for CMB observation. Then this Polar Bear project, fortunately, we are funded for some upgrade project, which is now called Simon's Array. And we also started some new endeavor based on Japanese technology. These are international collaborations in which we are playing important roles. But this Groundbird is a sort of a small-scale project based on the Japanese technology, including new superconducting detectors called the microwave kinetic inductance detectors. In the CMB, this microwave kinetic inductance detectors, or MKIDs for short, not yet used, but some people, including myself, believe that in the future, this MKID is going to play an important role in the CMB measurements. Then I joined the Calvi IPMU in 2014 as a project professor to promote this satellite project, Lightbird. And now, so this will come even after these ground-based projects. And we made an official proposal to JAXA last year, and then we hope to launch this satellite in mid-2020s. That's sort of a self-introduction. Now, let me give you some prologue about science. So by now, you see that I'm working on cosmology, and I'm an experimentalist. So my current research area is so-called experimental particle cosmology. So what is that? Well, this is shown sometimes. This is called the cosmic Ouroboros, showing the various researches in physics, depending on the scale of the system you are trying to understand. You see various, of course, tools and ways to understand these objects. But if you look at the largest scale here, this part is called cosmology. And if you go to the micro world and then go to the tiniest, smallest scale of the object, this physics is called the particle physics. Now, the essential point here is that cosmology and particle physics are actually neighbors. Why does this happen? One of the reasons is that now, because of the Big Bang, if you go back in time, the size of the universe gets smaller, but eventually although you are thinking about the largest object, you are forced eventually to think about the tiny objects. That's how this cosmology and particle physics are getting closer and closer. And that's why I say this particle cosmology, in which you need to think about both. And this particle cosmology seeks answers to the big questions in physics, but also beyond physics, actually. For example, the question like, how did our universe begin? That's a big question, obviously. And what fundamental laws govern the beginning of our universe? Here the remarkable thing is that if you look at the development of particle physics, you are on the track of unification of laws. That means at the beginning, you thought you had several different laws in physics, but later it turns out that these different laws are unified into one single, more fundamental law of physics. So then that is our ongoing particle physics project. So these big questions are what we hope to answer. And as I said, these big questions have, of course, a deep connection to our existence. So whenever you think about the real beginning of the universe and then everything started, and then here we have daily life here and we have structure, we have this, you have friends, and every existence started from one beginning. Can you imagine that? That if you think about that, you really, at least I really feel a sense of wonder. So this is still a physics question, but in a sense beyond physics. It's really even this sort of philosophical questions. And this is particle cosmology, and I said experimental particle cosmology. So the joy of experiments, at least to me, is that you can invent some new instruments. And history tells that the great invention often changed the world. And for example, the Nobel prizes for physics are awarded to some of the big inventions, instrumental inventions. Another sort of a practical joy you can experience is that you can see data. If you have built pretty nice new instruments, you can see data that no one else has ever seen. It's really exciting, I guarantee. Now, one striking fact about particle physics, because I have this particle physics background, I'm not educated as an astronomer. So my view is a little bit toward that end, but the one striking fact about particle physics is that we already have sort of rules with no exception, as long as experiments on the ground are concerned, which are called the standard model of particle physics. And obviously that's quantum physics, and sometimes we call quantum field theory. And so you have these elementary particles, quarks and leptons, and 4 fundamental forces And at least 3 of them are described with these gauge bosons. And this Higgs boson, that final special one, was discovered, as I said, recently. And this gives mass to each elementary particle and also gauge boson, except, of course, photon gluon. I'm not going to go into the detail of particle physics, but I just want to emphasize that many Nobel Prizes were awarded for the development of the standard model. So this is sort of a triumph of 20th century physics. No exception. Can you imagine? No exception, as long as ground-based, experiments are concerned. Now, but if you look up to the sky and do cosmological observations, some of the cosmological observations are incompatible with the standard model of particle physics. So in a sense, you already see the breakdown of the standard model of particle physics. And I show 4 things here. Inflation, which is the central theme of my talk today, which is accelerating expansion of the early universe. The second one is matter-antimatter asymmetry of the universe. We consist of matter, and then as long as we know there's no antimatter world observed. But in particle physics, it's very hard to create such universe dominated by matter. So this is an unresolved problem of particle physics. And dark matter and dark energy, Eric already touched on that. Oh, by the way, so Eric was so generous that he said, Professor Hazumi is going to tell us blah, blah, 50 times probably in his talk. So probably I should mention his talk 50 times in return. No, there's an approximate number. I'm an experimentalist, so good at having some approximate number. So dark matter, dark energy, these are not explained by the standard model of particle physics. So I want to emphasize this, in particular to the young students, that there are big riddles. The big riddles are in front of us. Nobody knows the answer for sure. There are some nice theoretical, studies and hypotheses, but hypotheses are hypotheses. So we don't yet know microscopic, for example, understanding of the dark matter. We are pretty sure that dark matter exists, but we don't know what. So in terms of particle physics, we don't know what dark matter is. Dark energy, it's really, we don't know. Dark, this wording, dark matter, dark energy, this might give an impression that cosmologists understand these things already, but it's totally wrong. Dark means sort of unknown, we don't know, or whatever. So that's why we're fascinated. That's why cosmology is fascinating, okay? You don't know what they are, and then you have a chance to really uncover the secret of the universe. You can continue and go even deeper. Another big question here. So there's another particle physics perspective at the beginning of our universe. As Eric already said, so I just said Eric at least once. So our universe is governed by general theory of relativity, or GR, invented by Albert Einstein almost 100 years ago. Note that GR is a classical theory with no quantum fluctuation. It's a classical theory. So, the second grade university students are learning classical mechanics. That means you can understand GR, right? Without quantum fluctuation, without quantum physics. However, the Big Bang, it's, if you go back in time, the size of the universe gets smaller and smaller. Eventually, you need to think about some sizable quantum fluctuations of space-time in the very early universe. Without introducing any concrete quantum gravity theories, this is the implication, okay? Well, still, I mean, those who know quantum physics, what we are talking about is quantum fluctuation of field, quantum fluctuation of particles. But now here we are just talking about space-time, which is different from just a particle. But the quantum principle basically is for observables. If you have some observables of space-time, you naively expect, that's something you need to verify with observations of experiments, but you expect that space-time also has some quantum fluctuations in the very early universe, which is not described by GR. So that's, in a sense, a breakdown of GR. So you need some quantum gravity. One famous example is superstring theory. I'm not gonna go into detail of string theory, but that's something people are really enthusiastic about. And then there are people talking about science fiction-like ideas of having some 10 dimensions and stuff like that. So, as I said, we have very interesting hypotheses about quantum gravity, but we do not yet know for sure what quantum gravity really is. So, from experimental point of view, we need some clever measurements to observe effects of quantum gravity. Well, at least we need to find a way to test quantum gravity theories, predictions. As far as I know, there's no such way of testing quantum gravity by using accelerator, for example, although accelerator is very useful central tool to understand particle physics. So by the end of my talk, I would like to convince yourself that cosmic microwave background, or CMB, polarization is our best hope. Okay, so by now you understand that by the end of my talk, I'd like to explain what we can do with CMB polarization. But before jumping into CMB polarization, let me just give some introduction to CMB. Eric already mentioned briefly about what CMB is. So instead of repeating that, I just first show this recent 100 years of development. In 1915, so this general relativity was invented, and then space-time curvature is determined by matter and radiation in space-time. That's the essence of general relativity. 1929, Hubble discovered this recession of distant galaxies, redshift, if you use the jargon in astronomy. So the natural interpretation of his discovery was that universe is expanding. And by the way, it might be interesting for you to take a look at original Hubble paper, and because it's based on several observations, it doesn't look really convincing. You see some points scattered around, and then you see the line. That was the discovery, and but she was right. And this is an example of recent measurements. You clearly see this trend, which you can call this Hubble law, because this is, I think, enough proof so that you can call it a law. So our universe is expanding. And 1965, cosmic microwave background was discovered. Actually, the discovery itself was 64, but the paper was accepted in 65. That's my understanding, by Penzias and Wilson. They were actually trying to do something else, whereas some smart physicists at Princeton were actually chasing this cosmic microwave background. But they used this antenna and then found some noise, first of all, in the sky. You can imagine that you have a nice telescope and point to many places of the sky. You always see some excess in your signal. Usual sense is that that's some excess noise you have in your system. So they also thought that way. They tried to reduce the noise in every possible way. For example, they found some pigeon inside this telescope, and then clean up, the telescope inside. But this noise didn't go away. Eventually, they convinced themselves that this is not from their instrument, but coming from the sky. But still, it's a little bit hard to believe. I mean, the nice thing about their discovery was that they really made every possible effort to convince themselves that this is coming from the sky. Otherwise, I mean, if you have some star and then see the signal, it's relatively easy to believe that something is there. If you have just same amount of signal, which just looked like noise, right? So it was hard to discover this, but they really had a great job discovering this. So they got the Nobel Prize in 78. So this was regarded as a direct evidence for hot Big Bang. I'm gonna come back to this later. Then in 91 or 92, there's a COBE satellite, which Eric mentioned in his talk in the morning, gave a much more precise measurement of cosmic microwave background. And then they got Nobel Prize in 2006. So two big discoveries were included in their work. One is to verify that the CMB just beautifully follows the black body radiation spectrum, which is consistent with the prediction of the Big Bang. The other is that they found tiny fluctuations in the temperature distribution of the CMB, which is called the temperature anisotropy. So that's
One moment, can you give us a little bit the connections in the past between the 65 number and the 1991 number?
Oh, between
Yes.
this time.
Just a little bit. Give us a little bit of the intellectual connection.
Right. So after this discovery, people tried to, obviously the first thing people did was to confirm this with different frequencies. And then, because then if you observe at different frequencies, you can have information about the spectrum of the CMB. And then these period was sort of an interesting period where people carried on using their own device, mainly on ground, to get some more pieces of information. So we have some steady progress these days. But this idea of launching a satellite was extraordinary because if you measure in space, you are really free from the effect of atmosphere, and you can have a much better measurements. Actually, COBE was not the only one. There's another satellite by Soviet Union, Relikt. Yeah. So, yeah. So, by the way, I was born in '64, but so I was not directly involved in the development during that time. But I learned from several people who experienced the development during that time that you had some steady progress, some small scale measurements.
Again, just for historical context, in this timeline where the Kip Thorne's Nobel was going to be sitting. Kip Thorne's Nobel Prize.
Talking about the gravitational wave detection.
Yeah, where is it going to be? In this.
I would say that's a little bit a different line. Yeah. So if you ask when, I mean, I'm pretty sure that was a big discovery last year. So you're talking about the LIGO discovery. So I'm pretty sure that at some point, maybe next year, I mean, they'll get the Nobel Prize. I'm not on the Nobel Prize committee, so I cannot be for sure, but it's a big discovery. That discovery itself is not directly connected to the cosmology I'm talking about here, but it's really a big step forward. So.
Yeah, you have to realize we are laser physicists, so we think LIGO is a success of the laser, not of the gravitational waves. So it's,
yeah, okay.
We have invested interest, to advertise that kind of work. And after $1 billion of taxpayers' money, we want to see a Nobel Prize there.
Okay. Yeah. So it's technology-wise, it's really amazing. Oh, by the way, I was asked to give sort of a. I mean, I was asked to focus on CMB in my talk today, but I asked to give another talk tomorrow. So more technical things, detectors, stuff like that, are not included in my talk today.
Oh, don't worry. That's fine. That's fine.
Yeah.
Will all be the talk of yours tomorrow.
Okay. So now, yeah, this is a proof of blackbody radiation and CMB anisotropy was discovered. That's an indication of cosmic inflation, which I'm going to talk later. Now, after going through the discussion session this morning, I think this is very introductory one. Still, I think it's worth for mentioning this. Eric already mentioned clearly what the expanding universe is, but nevertheless, I'm a little bit touching on this here. So here are some galaxies, and the discovery by Hubble means that these are expanding. You see this recession. But let me do this. You have these boxes in space where you see nothing, but you just write down these boxes so that you give some coordinate. In two-dimensional space, you have this longitude or latitude so that you can identify the position. So I don't know the exact longitude, latitude of Astana, but you can point the direction, point the location on the Earth. Likewise, in the three-dimensional space, you can write these coordinates, and then put these galaxies. So this is mainly for students, but if you think that you have some stationary space and then just galaxies are scattered each other, that's a wrong concept. What expanding universe means is that the space itself is expanding. So if you are on one of the galaxies, you're not moving. I mean, you stay in the same position, okay? You stay in the same position. It's as if suddenly the Earth starts expanding, the distance between Astana and Tokyo gets larger, but you are just staying in Astana, and my friend is just staying in Tokyo. So although you are staying, you're not moving. Then the distance between two objects is getting larger. That's the concept of the expansion. Then another important consequence of that is that if you have enough distance, this recessing speed can exceed the speed of light. Okay, you are told that the speed of light is the fastest speed in nature, but since you just stay in the same place, the recessing speed can exceed the speed of light. Okay. What's limited is if you change the location by moving to other places, this speed cannot exceed the speed of light. But as far as you stay in the same place, it's not governed by this special relativity limit. Okay, so that's yeah.
I ask you one question. Of course, you're quite right when you talk about the changing the distances between two galaxies due to the process of expanding. But what about the unit of distance measuring unit? What happens with this unit? Does it change or no? How it is possible to explain?
Physical distance. Physical distance is governed by, for example, you can use, say, fine structure constant. I mean, the electromagnetic interaction to define the distance, and that remains unchanged. The space itself, even without any material inside, is expanding. So in a sense, what GR says is that space does exist. Okay. So that's so to help your understanding, here's another example. So this spider web, well, this is after rain, so you can clearly see the spider web, but without rain, it's harder to see the spider web. Now, if you have some insect or whatever there, here, and if you pull this spider web, the insects or whatever objects stay in the same place, but the distance between them gets larger. Okay, this is sort of a this is a sort of idea, and then so even if there's nothing, no material, it's just an empty space that exists. That's the whole concept of GR, and this deformation of space. I was just talking about expansion, but this twist or whatever can happen. And then here's a famous example these days. I mean, GR was, when it was discovered, no one believed that it's anything to do with industry. But nowadays, this GPS is a famous example. You're using 4 satellites to point the location of you. I mean, this is a car, and it constantly modifies the calculation based on GR, because our space near the Earth is distorted. So as a result, clocks on GPS satellites are faster than those on ground. What I'm told is, you could calculate that, but about like 30 microseconds per day. And then without this GR correction, your GPS position will be like 11 kilometers away in a day. It's an astonishing example that even GR is useful for your daily life now. So, okay. Then expanding universe. Once you admit that the universe is expanding, the natural expectation is that the temperature of the material inside the expanding universe was decreasing. So then in a very early period, you expect that there's a sort of a plasma. So electrons and protons are apart from each other and form the plasma. But then after some period, you started forming the atoms, and then hydrogen atoms are shown here because the temperature got lower. And we now know that this happened when the temperature of the universe was around 3,000 kelvins. So this time was called recombination. So until then, this is just a sort of a lab physics. I mean, this is well-known physics. So in plasma, you have the electrons, protons, photons, and photons are interacting with the charged particles. Once you have this recombination, now you see just neutral particles. So photons lost, the chance of having interactions. So then after this recombination, photons just freely, travel. And this was really about, it's 400,000 years after the Big Bang. So then after that, these photons traveled almost freely. So that's we call cosmic microwave background. And as the universe expanded, the temperature further decreased, and then since the photons were inside that expanding universe, the temperature of the photons also got lower. So nowadays, we see that the 3 Kelvin universe. So from that, the size of the universe here and now can be also obtained. It's about 1,000 to 1. I mean, 1 to 1,000. So this was a discovery in 65, and so last year was anniversary, 50-year anniversary of CMB. So there's a conference in Princeton. So here Wilson is here. Oh, by the way, I'm here. So there are lots of CMB physicists, researchers there. So now about COBE, Eric already talked about COBE discovery, but didn't show this one, CMB temperature distribution. Or the horizontal axis shows the frequency, and this is the intensity. So you see that these data points are in perfect agreement with theoretical predictions, this solid line, which is a Planck distribution. And from that, you obtain that the temperature of this CMB is about 3 Kelvin. This is the exact number. So this was one big measurement that completely supported the idea of Big Bang. And this was already shown by Eric this morning. The Kobe also discovered this tiny temperature anisotropy of 0.01%. So what is shown here is that your average temperature is known to be 2.7 Kelvin. So you subtract basically this 2.7 Kelvin and then see what distribution you have. So this is a bit like, this surface just looks like a flat surface, but you just try to magnify this. By subtracting this average height, you're just interested in the tiny fluctuations. And then you could observe this fluctuation. Now, what is this CMB temperature anisotropy? So, first of all, CMB is the oldest light. As I said, before recombination, the universe was in a plasma state. So the photons were really scattered around so frequently that you couldn't get that information of that era. So CMB is the oldest light. Because of that, you can view that the CMB anisotropy is regarded as the initial condition of structure formation at later times. The structure formation means you see galaxies and you see us and all the structure, a great structure in the universe nowadays, but it started from this tiny anisotropies. So because gravity pulls things together, so at the beginning, even if you have this tiny fluctuation, that could evolve into the present structure of the universe. So in that sense, since this is the oldest light, CMB is the oldest light, that's regarded as, this anisotropy is regarded as the initial condition. Even more, as I said before, the Big Bang implies quantum fluctuation of space-time in the very early universe. That's actually, I'm talking about the time earlier than CMB generation. Okay? So if you combine these two things, you can say that CMB temperature anisotropy implies that the origin of our existence is quantum fluctuations. So at the very beginning, you imagine that there is some quantum fluctuation of space-time. And that was the real seed of our universe. And then at the time of recombination, you observe this CMB anisotropy. But the origin of that, we believe, is the original quantum fluctuation of space-time. So quantum physics was discovered in 20th century, and we have huge amount of experimental evidence on quantum physics. And we really live in a quantum physics era. But until this discovery, nobody really convinced that the origin, our origin, is quantum fluctuation. So, I mean, when quantum physics was discovered, nobody thought about that. So, this is a sort of let me allow to be a little bit dramatic. So, at the beginning, quantum fluctuation of space-time existed, and that gave an initial condition of structure formation. As a result, we live here today. So this is...
Professor, for some of us that we are kind of doing tabletop experiments and tabletop calculations, like quantum optics people, we really understand what quantum fluctuations are. Produce kind of Casimir effect. They produce some very nice things.
Mm-hmm.
but really going from this kind of, if you want, quantum chaos to Astana is a little bit, too of an aggressive leap, don't you think?
But what I can say is without this initial condition, we're not living here, right? So you're talking about nonlinear evolution and all stuff like that. That's of course, different story. I'm not going to say that the cosmology can explain everything on biology or whatever. I'm not saying that.
No, you're a physicist. You will never do that kind of a crime. We believe you on that. But still, just saying that quantum fluctuations that we don't really very well even understand, even at the level of when we're trying to essentially estimate what is, Casimir forces between the two capacitor plates that early universe, a city, is very, very intellectually ambitious.
I'm not saying that we can understand this structure based on the first principle equations. I'm not saying that, okay? But what I'm saying is that the existing of us started from this quantum fluctuation of space-time. I mean, when quantum physics was discovered, no one, I guess, believed that this quantum fluctuation at the beginning was anything to do with our existence. But now our modern cosmology tells this amazing picture of the universe. So that's something I want to emphasize.
Quantum fluctuation of the space-time or quantum fluctuation of fields in the space-time?
We believe that we need this quantum fluctuation of space-time itself, in addition to some, I'm going to touch on that, but we are sort of forced to introduce some new particle fields to explain the beginning of the universe. So we believe that we had both quantum fluctuation of fields and quantum fluctuation of space-time. Yeah. But the even dramatic thing for me is that you have a chance to distinguish between the quantum fluctuation of particle fields, which we believe is scalar field, and quantum fluctuation of space-time. So by experiments, by observations. So that's what we want to achieve. Now, so I explained up to the COBE discoveries. Nowadays, we have more projects. As Eric said, so the WMAP was launched and did great measurements. This was launched by NASA. And in this century, Planck by ESA was launched. And then still, we are getting some more new results from Planck nowadays. And on ground, we have large telescopes, one at South Pole, SPT, the other in Atacama, ACT, Atacama Cosmology Telescope. Because these dishes are pretty large, these give much better angular resolutions than these satellite projects. So here is an example of temperature fluctuation from Planck, and you see this big improvement in angular resolution and also actually the precision and accuracy of the anisotropy. So in order to understand better this, and in order to compare this with theoretical predictions, we do the power spectrum analysis. And here's a nice demo by ESA. So I just show this one. ESA is a European Space Agency. So they made this nice 2-minute presentation about power spectrum calculation. So here is a power spectrum, and this horizontal axis shows the angular scale, angular size. So what you do is that once you have this fluctuation, you have this. This is in a you can just analyze it using spherical harmonics. I mean, in a one-dimensional function, you can just analyze it with Fourier decomposition. In 2 dimension, for this measurement, you can use the spherical harmonics. Now, these are with a larger angular scale, and so these are for smaller angular scale. So basically, by doing this analysis, you can obtain this power spectrum. So, and that's really a nice summary of what has been observed. And then these specific peaks really demonstrate that we had a hot, dense plasma made of photons and baryons, and then that had some so-called acoustic oscillations, because of gravity. If you have a dense region where you have more particle, it's becoming denser. But then you also have radiation, and then at some point this sort of a repulsive force by radiation wins. So in that way, you have this sort of oscillation. That's the so-called acoustic oscillation. But still, that's not enough. That's why this temperature, CMB temperature anisotropy, is so fascinating. Here's a nice demonstration by the WMAP. So this is a standard cosmology fit result for WMAP data, which beautifully agrees with data. This red line shows the theory, and black dots are data. It's a beautiful agreement. So if you say, I don't believe dark whatever, you just believe atoms. You put 100% of atom in the universe and then see what happens. So then this evolution, then you can go through the evolution, and then you end up having this power spectrum, which is completely incompatible with data. So it's impossible to explain this data just with atoms or ordinary matter. Likewise, you say, okay, I admit that dark matter exists, but I don't like dark energy. I don't believe dark energy. So you ignore dark energy and then see what happens by putting this dark matter. Still, you see this distribution you end up having is completely incompatible with, different from what you obtain from measurements. So, whereas once you put correct energy ingredients, you see the beautiful agreement. So, the primary reason of this great success is that the evolution from the beginning till the time of recombination was really linear. Whatever system you have, if that's a linear system, you have a good prediction. Whereas if it's a nonlinear system, it's pretty hard. So it's really hard to predict the weather tomorrow, right? Depending on the situation. But whereas it is, this is really the signal from the beginning of the universe, but you have a beautiful understanding and agreement between theory and experiment. That's the beauty of this CMB. And another. This is lambda CDM and FLW. This is, yeah, this is lambda CDM, yes. Yes, yes, yes. So, another reason, even if you have this nice linear evolution, after recombination, if CMB was affected by some non-linear effects, you should have lost the information you had. Whereas, as I said, once recombination happened, the CMB photons traveled almost freely in space. So in a sense, the information was frozen and then delivered to us. So that's because of these two reasons, CMB is really, really important, I would say, central tool in cosmology. And Eric already talked about this energy density of our universe. So dark energy dominates, and dark matter is much larger than ordinary matter. And that's mainly thanks to this nice CMB observations of temperature anisotropy measurements. And another thing you can obtain is the age of our universe. The position of the first peak is a key piece of information, and that tells you the sort of a size at the time of recombination. And then from that, and you need to think about the ingredients of universe, the dark, in particular dark energy, dark matter, as discussed by Eric already. And then from that, we obtain this precise number for the age of our universe. So I would say cosmology, thanks to CMB temperature fluctuation measurement, cosmology is now exact science. And then this is a temperature anisotropy in a little bit different horizontal axis definition, but basically the same thing I already showed, and then that also includes contributions from ground-based projects I mentioned, ACT, SPT. So these fits are done just using 6 parameters of the standard model of cosmology. Note that this is different from standard model of particle physics. Because as I said already, dark energy, dark matter, stuff like that are completely outside the standard model of particle physics. Okay, so we can make this beautiful fit just using 2 parameters. Out of that, 6 parameters. Out of that, 2 parameters are related to the initial condition of universe. The other 4 are related to the ingredients and the evolution of the universe. So just 6 parameters. So it's a triumph of temperature fluctuation measurements. So since discovery until now, this is 50 years of history in a very simple way. I'm summarizing this temperature fluctuation golden age. It's ending now because Planck has done almost the best measurements. You cannot really improve that anymore. Whereas we're talking about the radiation. So, radiation has intensity information and frequency information and polarization information. Okay, 3 ingredients basically. Polarization is not yet measured precisely enough. So, and since if you think about this glorious history of CMB, probably that gives you a good enough reason to believe that polarization fluctuation is the way to go. But you have more actually to believe why CMB polarization measurements from now on are the new frontier. So I'm going to the real beginning of the universe and talk about cosmic inflation. This inflation hypothesis was sort of discovered in early 1980s. The essence of this hypothesis is that our universe went through accelerating expansion before the hot, dense Big Bang state was created. It sounds like a crazy idea, but that resolves some outstanding problems of the naive Big Bang model. I mean, Big Bang model is very successful, but naive Big Bang model has some issues listed here. So horizon problem is, sorry. Oh, so this is, sorry. Oh, by the way, these three people were awarded a Calvi Prize 2 years ago. But as a Japanese, I also wanted to add this Katsuhiko Sato's contribution, which was also important in establishing the idea of inflation. So, horizon problem, what does that mean? You know, the CMB temperature is almost the same everywhere. I mean, except this 10 to minus 5 fluctuation. Can you really make that happen? I mean, this place and this place in the universe send light to us. And now we see that light, okay? Could these places talk to each other before? It's so distant that the naive expectation is no, they couldn't. So in a sense, that means some remarkable fine-tuning should happen at the beginning. It's like, even if, I mean, sometimes I do some small experiment with the audience. I mean, I ask everybody to close their eye and then raise your hand at any time you like, and then see if you see the moment where all the guys in the same room raise their hands at exactly the same time. And that's tough, right? So unless you really communicate with each other. So although naive Big Bang is a great success, it's hard to explain why two places which seemingly out of contact before do the same thing. And this enormous accelerating expansion of inflation is a sort of a brute force answer to that question. So what that tells us is that at the initial condition, everything is in a small enough place in which we could have some contact with each other. The photons travel through this place. And at one point, suddenly, it expanded. Now, it's so sudden. Now, this place and this place looks out of contact. If you had this situation at the beginning, you could explain what we are observing. But typical inflation theory is really it really looks crazy, because what you need is something like this. The universe could expand this 10 to 26 times in 10 to minus 38 seconds or so. Nothing could allow us to do that. I mean, within standard physics. Okay, even more. So Eric introduced this scale factor, A, in the morning. The scale of our universe is expressed by just one quantity, A. So what do we know about time evolution? So here's the equation we have for general relativity. I'm not going into detail, but the point is that if you impose this cosmological principle, which is that there's no special place in the universe, you just have one parameter in the equation. So what I said here is that we need this one quantity physical quantity to show the scale of our universe. And Einstein's general relativity supports that idea if we impose this cosmological principle. And then you can even have this quantitative Friedmann equation. Then you can have this A dot is positive. That means expanding universe. Now, as Eric already said, the problem is that if you talk about the second derivative, time derivative of A, you end up having this, and here you have pressure, and here's minus sign. And it's known that with known matter and radiation within the standard model of particle physics, you always have this. A dot dot is negative. Which means you cannot create this situation, expanding universe, unless new field. So now what you have done here is you are stubborn. You try to believe general relativity and particle physics, known laws of physics, and see what happens. You saw what happens. What happens is that you are sort of forced to introduce something new. So it's another way to look at the breakdown of standard model of particle physics. Now, so you're forced to introduce some new particle. And then once you admit that, then you're a theorist. You can freely play with some equations, some new particles. And then the typical way is to introduce a scalar particle called inflaton. Not inflation, this is inflaton. The simplest model is to introduce just one inflaton. And this needs to be tested. Since this is the simplest model, we like that very much. So inflation with just one inflaton is, so to speak, a standard model Higgs in cosmology. Indeed, if you look at Lagrangian, it's really similar to the Higgs Lagrangian. It's a spin zero particle, and then it does really accelerating expansion. So once you admit that accelerating expansion at the beginning, you have another consequence, because you have at the same time quantum fluctuation of space-time. Once you allow this accelerating expansion, this quantum fluctuation was sort of frozen to be realized. So one particle physics point of view to understand that, which was introduced by Caldwell Kamionkoski in this article, is to see that you have gravitons, that's sort of particles carrying gravitational forces, then they were pulled apart much faster than any other situation. So it was created as a virtual particle, but then became real particles. I know it's a bit sloppy way to explain the situation, but it helps understand what's going on. So you are forced to think about acceleration at the beginning, and together with that, if you have this quantum fluctuation of space-time, that was sort of much expanded and realized.
So to observe or to observe gravitons,
Yeah.
what will be the experiment?
It's a very good question. I really hope to observe gravitons one day, but it's hypothetical particle in quantum gravity, and nobody has really observed that. So as I said, this quantum gravity is a big theme in physics, and it's really hard. So
I understand that, but all of us who are physicists, and the definition of a physics person is, how do I measure any theoretical idea? I think that's
Right.
what at least I try to teach in my classes,
Mm-hmm.
and try to do in my work. So if the graviton is never going to be found in the next billion years, does it exist?
Next billion years, I don't know.
You understand what I'm saying?
Yeah.
It is beyond the resolution, of the humankind.
Actually, you don't need to introduce gravitons. I introduced gravitons here just for the aid of understanding from particle physics point of view. What you hope to measure is, maybe I should, what you really hope to measure is this gravitational waves emitted during the inflation. That's what I'm going to tell you. So because of this situation, we believe that the emission of primordial gravitational waves occurred. So the big question is there any way to detect primordial gravitational waves? Here, luckily, the answer is yes. We have a chance to detect primordial gravitational waves using CMB, but this time polarization. So let me talk a little bit about the physics at recombination more. At the time of recombination, you had photons and electrons, protons. So if you look at one electron here, and here are some incoming photons, radiations, and you expect some scattering here, it's textbook physics, Thomson scattering. So it's polarized. But if you have exactly the same amount of photons into electrons here and there, the net polarization is canceled. However, if you have this configuration, some hot regions here and cold regions here, you see non-zero net polarization. Okay, this is just a textbook physics.
May I ask one question?
Yeah.
Yes, I know this rather well about the physical reason of the process of polarization. But what can you say about maybe one new mechanism as Faraday rotation, due to any magnet field, magnet field of large scales, and maybe this magnet field leads to the process of polarization.
Oh, you're asking a magnetic field?
Yeah. This is from one side, and other possible mechanism. This is universe rotation is total.
Okay. So the possibility of having some primordial magnetic fields, for example, is not well understood yet. So there is a remaining possibility that there are some mechanisms to create primordial magnetic fields, and that affected the CMB polarization. That's a possibility. There are some constraints already from data, but that's a sort of an ongoing theme in cosmology. It's a sort of a non-standard possibility, but it's not yet completely ruled out.
Maybe this mechanism will be the most pleasant in this case.
Okay, so once you know that some net polarization, non-zero polarization can be seen, then you think this way. So suppose you have a very nice polarization, CMB polarization measurement on the sky. You expect to see some pattern. Now, the difference between this polarization and temperature is that the polarization has this directional information. Temperature, you have just a size. Okay, so it's a bit like water flow, where you can expect some, curl or divergence and stuff like that. You can define divergence and curl. So we have a jargon for the divergence. We call it E mode, and for the curl pattern, we call it B mode. So once you have nice measurement of CMB polarization, you can analyze that and then decompose that into sort of a divergence and curl. Just like when you have a nice measurement of water flow, what you do first is that at each point of water flow, you know the velocity of the water. But once you have that kind of information, you can analyze that field to obtain some divergence and the curl. So it's a bit like that. And okay, so this, I said two things. One, at the time of recombination, you could you expect some non-zero polarization in the sky. And then number two is once you can have nice measurement of CMB polarization, you can decompose that into E mode and B mode, or divergence and curl. Okay, so now one important thing is that this last scattering, the recombination, sorry to introduce more jargons, but last scattering basically means recombination here, occurred in the primordial gravitational waves. The primordial gravitational waves were created at the beginning, remained sort of background gravitational waves. So here, probably I should say what gravitational waves are. It's, say, a bit like an earthquake wave. Ground looks really solid, and then doesn't look like producing earthquake, and then the waves propagating in the ground. Likewise, the space itself, actually it looks empty, even doesn't look solid. But you already know that it can expand, it can twist, it can be twisted, so it can propagate this the difference of the scale factor, or twist or whatever. So that's called the gravitational wave. Okay. Yes, perturbation. So then it's actually gravitational waves are described by this metric in GR, which has two legs. So in a sense, that's sort of a spin 2 state. And according to the general relativity, you can have this wave equation from that. So this is a typical example of the gravitational wave mode. You can imagine that the space here is really this contracting and stretching like this. And that wave can propagate in space. Now, if you have this gravitational wave in space, the contracted place can be regarded as a hot state in here, where you expect more radiations generated and coming into the electrons here. Whereas the stretch part is regarded as a cold part. So if you have this propagating gravitational waves in space, and then think about this sort of gravitational wave, stretch and contraction, you can expect this sort of hot, hot, cold, cold, hot, hot, cold, cold, hot, hot, cold, cold configuration. So what was shown here was that if you have this hot space, hot region, cold region, cold region, you have more radiation coming from hot regions. As a result, you have non-zero net polarization like this, which I call it a hot sand, because the hot, hot, and then this polarization direction is along this way. So you can, if you have gravitational waves, primordial gravitational waves propagating in space at the time of recombination, you could expect these polarization along with the gravitational waves. Now, you can think about this situation. You have gravitational waves this way, this way, this way, this way. And then when you extract the net polarization here, 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 like this, you see now curl pattern made out of these gravitational waves.
By the way, does this your fingers?
Yes, I made it before I came here. So this is one particular example, and gravitational waves are floating in any direction. But the point is that it's impossible to erase all the curl patterns in space. So you should always expect that you have some remaining curl patterns from this primordial gravitational waves. So this is really, I know I'm really talking about very complicated, nice mechanism discovered like 20 years ago. Until then, we didn't think about this nice possibility of measuring the effect of gravitational waves, primordial gravitational waves. But this is a simulation. Test. This is sort of a test pattern on CMB. And then if you see this, for example, wherever, here, you see some curl pattern like this way. And here, you see some curl pattern in the opposite way. So that's why we put this red color here, blue color here. The point is that once you have nice measurements of these polarization pattern, you can reconstruct these blue and red pattern. Now, then you see just like temperature, this is a B mode fluctuation pattern on the sky. And by doing a spectrum analysis of this, you can compare this pattern with inflation theory, which predicts the primordial gravitational waves. So that's the essence. And then let's see. But before coming to the possibility of observation, I just show one more thing, which is reionization. I said after the recombination time, universe became neutral, filled with hydrogen, and it's like transparent. CMB photons traveled without interactions. But it's almost true, but not completely true, because the universe continued expanding and cooling and then structure formation. And at some point, we know that there's an era of so-called reionization, in which, because of this hot gas states evolved, hot electrons emerged again here, which created some rescattering of CMB photons. So in a sense, universe is not completely transparent, a bit opaque. That's something you need to remember. Actually, one more thing, sorry. Another thing is another possibility of having a curl pattern, which is called lensing B mode. So here is recombination. At the recombination was a sort of a time of last scattering of photons. So we sometimes call it the last scattering surface. And I said this photons just travel freely to us. That's true, but still, during the course of this travel, there are some gravitational potentials that bent the course of the photons. So you see, if you have some perfect symmetric so-called E-mode pattern at the beginning, if you have this bent, you see it's a sort of a observation through imperfect lenses. So you have some dislocations. As a result, you expect to create some B-mode curve pattern. That's a secondary effect. So I know I'm talking about real sort of a real it's a CMB polarization research topics, which might be too much for second grade students, but still, it's really fascinating. So I'm continuing this, and then so this is the B mode, expected B mode power spectrum. You see this pattern is predicted for primordial gravitational waves. This one, this peak is from recombination. Another peak here is for reionization. So we expect two peaks. And then the third one component is from lensing. So I explained that during the recombination period, due to primordial gravitational waves, you expect to have some curve pattern, and the fluctuation of curve pattern can be analyzed, and then you can get this power spectrum. But that's not the whole story. You also expect the contribution from reionization, shown here, and also you expect the secondary effect, lensing. So the game here is to really measure this. And this is not the latest status of measurements, but this shows measurements of E mode, which you expect even without inflation or primordial gravitational waves. So once you really obtain success, if you succeed to obtain this distribution, you can measure the intensity or height of this power spectrum, which is shown with this problem. So for larger R, you see bigger intensity. For smaller R, you see a smaller intensity. This is proportional to this cosmological parameter R. One amazing thing, if you really succeed this, you can test inflation theory, because when you say inflation theory, behind that you can create many different types of models. And then each model has different sort of potential energy in the model. But this potential energy is proportional to this R you can measure. Okay, so if you really succeed to measure this, this is going to be a historic discovery, and then it's direct evidence for cosmic inflation, and it's related to the ground unification scale physics from this formula, and arguably the first observation of quantum fluctuation of space-time. So I cannot really see gravitons, but I can see the quantum gravity effects from this measurement. And this endeavor is going on. This is the current B-mode power spectrum measurement result. Ignore these upper limits in the past. Now we see some measurements touching on this lensing B-mode. Unfortunately, this is not from inflation. This is from this gravitational lensing. So what we really need to see is here, but we haven't really touched on this part yet. But just from this, you can also set some limit on the size of this R or size of primordial gravitational waves. One of the examples I'm working on is this polar bear and Simon's array collaboration. Polar bear touched on this part in 2014, these red points. And that's a telescope in Chile. I don't go into detail of the equipment, but this is sort of a observation in one night. Of course, it's much smaller in reality. It's just for one night in like 10 seconds. It's, by the way, it's really, you can enjoy the beautiful sky in Chile like this. You can take this sort of picture just with your camera. So I'm becoming to the end. As I said, you can already obtain some constraint on this R parameter and test actually inflation theory, some of inflation models. So here, what this figure tells is that R cannot be so large. Actually, R, for some reason, this is.
Take a brief interruption. So I have
Sure.
Professor Smoot on Skype.
Oh, okay, sure.
So
I'm nearly ending, but yeah.
He'll say a few words and then we'll go right back to
Oh, okay, sure,
okay?
sure.
So let me see if we can.
I have just a few more slides to end, but yeah, it's okay.
Like 3 or more? What's?
It's like a 3.
Three more?
Yeah.
Okay.
Something like that.
I think yeah, he has to go before 6 o'clock.
Okay.
So why don't you finish off?
Yeah. Okay. So what's remarkable here is that some simplest model here is already ruled out. So some people really hope that the simplest model here, simplest model of inflation is correct, but it seems it's not true. But it's amazing that, and then these models have some idea of quantum gravity behind that. So we are really entering the era where we can test quantum gravity. So, which was seemingly impossible before. And there are so many projects running and in a planning stage. I'm not going into detail, but for example, we are working on this polar bear, which will be upgraded to Simon's array. The Simon's array will be merged with this octopus to form a new Simon's observatory, and eventually in 2020s, we expect to have even more powerful ground-based project named CMB-S4. So there are many activities going on ground and also balloon. And if you look at satellite proposals, we have these three, and Lightbird is what I'm pushing for right now, which passed the initial down selection by JAXA. So we are in a phase A stage, and there's a proposal expected at the end of this year, PIXI, and also in Europe, this ESA M5 mission was recently proposed. These are for ultimate measurements of CMB B mode. For example, I showed this current situation. With Lightbird, we expect to have this very precise measurements. So that's a bright future. And I know I'm skipping the science shopping list for Lightbird. Just go to the conclusions. It's a very simple conclusion. So experimental particle cosmology is so exciting. I changed my subject, and then so far I have no slightest regret my choice. And then CMB polarization is a new frontier chasing this test of inflation and the quantum gravity. I'm sure that the discoveries await us, and as I said, big riddles are in front of us. So in particular for young students, I would say join us. Thank you very much.
Okay, so we're going to connect. We're going to try to connect, and then we'll come back to questions.
Sure.
So let me just.
And then we can
come back for questions and
come back to
discussions.
questions and discussions.
So one of these computers have to be moved to one of.
Oh yeah, here we go.
All right, George, you are. Let me move the little window. You are live. Let me. Oops. Let's get through this.
I didn't mean to interrupt so much, but we originally tried to schedule the meeting on an hour ago, but the schedule got changed around. And unfortunately, I have to leave fairly soon to go to a dinner. I'm in Hong Kong right now, and we have events going on today, although I'll get a chance to try and call in tomorrow. But I've been listening to Mahasi's talk, and I first wanted to thank him for coming and giving the talk, but also it reminds me of all the stuff I've been doing for a long time, because it was 20-something years ago that I with Mike Turner and Paul Steinhardt, we wrote a paper saying looking for the gravity waves would be an important way to test inflation. And now we're getting close to do that. And that's kind of exciting. But it's what's interesting is it's become a worldwide endeavor, and so seeing the Lightbird, seeing the polar bear. What you didn't mention was the CMBS-4 mission that will be coming along, and presumably we'll talk about it later. The de-lensing of the E modes, so that you can look deeper for, say, the B modes. There's a lot of activity in this area, and many people wanting to see this happen. So first of all, let me thank Azumi-san very much for coming and giving the talks. I'm sorry I can't be there, and I also want to say that I do want to have a chance to talk with you again later, because I've been putting proposals in to help support activities for Lightbird, but also for other things, and so we can talk about that. So not only are we doing things in Kazakhstan, but I put proposals in Europe and in France and Hong Kong. So hopefully we'll get a chance to talk about that. But I want people to understand that this is a very exciting area, and Azumi-san is very up to date on this and leading what I consider to be one of the most major efforts. And we wish him the best luck in that, and any way we can to support him and help participate in it so it goes well. So thank you very much.
Thank you very much, George. Yeah, for kind words, and I really enjoying my stay here so far. So, yeah.
I'm sorry that it's a little cold now. It's very warm. It's very warm right now in Hong Kong.
Oh yeah, I see the difference. But Eric gave me advance notice, warning. So I have enough warm clothes.
So that I would, because I had stuff scheduled earlier in the day, then I have a dinner that I have to leave for in just a few minutes, and but I wanted to say with it, and then I wanted to get a chance to talk with you because I talked to you before about this, but now I'm saying, well, people in Kazakhstan would be interested in participating and doing work with you and with CMBS4, and so will people in other places, and so the question is, how open is this going to be? I think we should encourage people to be involved in these kind of activities. It's a good worldwide activity. So.
Yeah, I agree.
And tomorrow afternoon, Masashi will be talking about the advanced detector development, which has good ties with what we'll be doing in the laboratories here at Nazarbayev University. And if possible, that we can get you to Skype in again tomorrow afternoon, then that would be...
That because we've been building up the lab in France to do the MKID detectors and to do the readout, the electronics. I don't know if Lightbird, you've actually worried about the readout. I mean, we've been doing the stuff for the Roach boards in Berkeley, and we've been trying to upgrade that in Paris. We'll see when that happens. And we're talking about doing that and the optics in Hong Kong, but we have to, talk to you and see what does Lightbird need. We know what some of the other things need, right?
Mm-hmm. Sorry.
And there'll be opportunities.
The thing to concentrate on at the workshop there, and I hope everybody's enjoying it, is the science, and then the stuff that Azumi-san will talk about tomorrow, which is the technology, the advances in the devices and advances in the techniques and engineering that it takes to make measurements. One of the things you'll see is, compared to what we were doing 30 years ago, we're more than 1,000 times more sensitive than we were when I started. The first experiments I did, we were looking for things at a millikelvin. Now we're doing things at the microkelvin, and we're going to aim to get down to the nanokelvin level. So the improvement in sensitivity that we're doing in the cosmic microwave background is equivalent to the Moore's law improvement in computing power.
And I think there'll be opportunities for the students and the engineers and the researchers here at Energetic Cosmos Laboratory, at the physics department, engineering departments at Nazarbayev University to work really, really hard, but also do very, very exciting science. Yeah. Okay. So thank you very much, George. Here, I'll turn you around so you can see a bit of our audience.
I get to be in the warm weather. You guys get to be in the cold weather.
Yes. All right. So hopefully we'll be able to talk to you tomorrow as well.
All right, we'll try and plan that. I think tomorrow my schedule's a little better.
Okay, very good. Goodbye.
Bye.
Bye.
Okay, you can plug back in.
Okay, and now we can make questions.
Yeah, so we have some. Any questions and comments and suggestions? Okay.
Dr. Kazumi, the most unclear thing to me was so polarization. Does it change with time or with any other property, or does it stay the same since the Big Bang, and it depends only on the angle of the coming incident particles?
That's the polarization of CMB
Yeah.
was determined at the time of this recombination, last scattering, as I explained. And zeroth order, then this information was frozen, just delivered to us. So we are really, in a sense, directly seeing the universe this 400,000 years ago, years after the Big Bang. So that's a zeroth order answer.
Do you want to mention something about reionization and probably the formation of the first star?
I put that in because actually, maybe that was too much, but I put that in. So once reionization, the hot electrons were recreated, that can disturb the CMB photons again. I mean, scattering could happen again. And then that's exactly the same situation that we had during recombination, scattering of photons on the electron. So then you can create the curve pattern again, but at much later time compared with the recombination, and much sort of, in a sense, closer to us. This is much bigger pattern. So that's why you have two bumps.
But how much time does that returning to the initial pattern? How much time does this?
Or you don't maybe?
The reionization is like 100 million, at least 100 million years after the Big Bang, you know. And so that's much later time compared with the recombination time.
Maybe, but I want to know the magnitude of angle of the plane rotation, magnitude.
So again, the zeroth order, it's unchanged, but probably you're worrying about some possible effect of magnetic field or whatever, and Faraday rotation and stuff like that. Yeah, I mean, for the central frequency of CMB photons is 160 gigahertz. For that, effect of, say, Faraday rotation is very small. So that's.
This is my favorite theme also.
Okay.
When you are talking about fluctuations of the spacetime, is it fluctuation of the matrix or spacetime?
Sorry.
When you are talking about fluctuations of spacetime, you are talking about fluctuation of the metric.
Yeah, actually, that's
because
what I mean.
fluctuation of the spacetime is something different.
Right. So
this is quantum wormholes and so
on. Yes, there's a matrix. Let's see. I showed some equation here. Yeah. So this is a gravitational wave equation here. Yeah, you see this H cross, and you know, these you can introduce. So basically, you can introduce commutation relation to that quantities to introduce a quantum fluctuation. I mean, within GR, classical theory, you should not have that kind of quantum fluctuation. So that's, I mean, the commutation relation should be zero, obviously. But you can introduce a commutation relation just like ordinary quantum physics. This is because this is a physical quantity. You have freedom to introduce that. And then the great thing is, yeah, so actually from experimental point of view, that's something you really want to measure because nobody has really seen that space fluctuation, quantum fluctuation yet. But I mean, this is, so you might argue that this is sort of a hyper or super application of quantum theory to space. But if you look at this is a, wave equation, and then it's a natural thing to try to introduce a quantum fluctuation for this physical quantity. Yeah.
Just please, can you? No, I mean we had a recording. That's why we needed.
Could you repeat how we distinguish the E and B modes created by these initial gravitational waves with the other E and B modes that are created from farther later, from when we have again the rethermalization of electrons?
Right. So we have. So let's first focus on this time of recombination. So you can just from temperature fluctuation, you can create this sort of pattern, but it's known that just from this temperature fluctuation, you can only create this so-called E mode, which is divergent part and has even parity. So what is actually really important is that if you ignore the B mode from lensing, you can create this curve pattern only from gravitational waves at the time of recombination. That's a zeroth order understanding. And although I didn't say this, actually that primordial gravitational waves, I mean the distortion of space-time at the time of recombination, created both B mode and E mode actually. So the point here is that just from temperature fluctuation, if you don't have gravitational waves, you could only create E mode. So in theory, you can also search for primordial gravitational waves from E mode as well, but it's much more contaminated in a sense. Whereas this is a pure gravitational wave signal. Again, right now I'm just focusing on recombination time and ignoring later time. That's a later stage, and so the question is it possible to distinguish between two B modes, one generated at the recombination time due to primordial gravitational waves, the other from this lensing, this bent of photon travel path? The answer is yes, actually. If you look at this power spectrum, the shape is different. So by having this, you can basically distinguish between lensing and the primordial two components. And by doing, I mean, that's actually George mentioned the delensing. That's actually one technique to distinguish between primordial part and the lensing part, which is So a lot of people are doing this, working on this de-lensing studies. And
Any questions? Okay. If not, thank you, Professor Hazumi, for your
Okay,
presentation,
thank you.
for a talk. And I think we have some questions during the coffee break. Now we have a coffee break in this is in our canteen. Please welcome to the coffee break, and just we start at 4:30. 4:30, and Professor Chechen will give a talk about 10-20 minutes about the glass fermentation of accelerating dark matter background. To take a coffee break, to take a relax in 30 minutes. part of afternoon session. The Professor Leonid Chechin from Fesenkov Astrophysical Institute will give a talk about galaxies' rotation on their acceleration dark matter's background. So please, you can start. You have a 20 minutes for talk and
Yes,
5 minutes for...
I remember.
Okay.
Dear colleagues, I'm very glad to see all of you once again. Many apologies to, thanks to Nazarbayev University. I want to introduce my young colleagues. Dina Karat-Kazy, stand up. This is, and, sorry. And this is Talgard Konzbayev. What? So this is our common report about the title. You see the galaxy's formation. What is the physical essence of this theme, and what for we consider this problem? The answer may be as follows. Oftenly, everybody knows that galaxy consists in principle of two main parts. This is baryonic component and non-baryonic component, or dark matter component. And the ratio of their masses about 9. That is why this means that the most part of the galaxy, we are talking about the mass, depends on dark matter. That is why we are considering the new form of dark matter. Because oftenly dark matter have been considered as the stable matter within which some different astronomical processes were elapsed. And from other side, it is necessary to take into account that this vision or position that dark matter is a stable one, of course, maybe not very adequate to the real physical situation. And for doing this, it is necessary to consider other more realistic forms of dark matter. In our case, we are considering the oscillating dark matter. What is the physical essence? How it is possible? What is the physical essence or physical reasons that we may consider the dark matter as oscillating one? In this slide, you see the process of interacting of two galaxies, and of course, the dark matter components interact between themselves, of course, and that is why it is possible to consider the interaction as any physical reasons for considering that our dark matter may possess some oscillations. In this slide, you see the scheme of the oscillating dark matter. And of course, this is the most simplest figure, the most simplest pattern. And when we are considering the dark matter, that consists of number of right circle rings. We have any physical reason that allowed us to consider the dark matter as the oscillating one. So that is why we have deal with two component, baryonic and non-baryonic. And if it's so, it is possible, it is necessary to consider some mathematical equations that allowed us to consider the process of their interaction. The simplest case, when we are considering, for example, one substance, this is well-known Jeans equation. For considering this equation, for solving this equation, and for getting some physical reasons, for getting some physical consequences from this equation, it is necessary to decompose every physical value that introduced in this equation. This means rho dark matter density, its velocity, potential, and the pressure in the Taylor series, and we are considering as it as a plane wave. But when we return to our problem, we are considering as minimum two components. That is why it is possible. In this slide, we write down the generalization of Jeans equation for the case of n component. This is in this case you see in this slide you see that P, this is pressure that depends on baryonic matter from one side and maybe other components, and the same with respect to density. But when we are considering the galaxy, that depends on baryonic matter, consists of baryonic matter and non-baryonic matter, dark matter. That is why we are considering only two substances. And in this case, we have the following system of equations that is necessary to consider the previous scheme any unknown value. In this case, we have also five values, and we are decomposing on the plane waves as in previous case. This delta x that depends on t describes the process of depending these physical values on time. So I must say the following, that at our previous work with another my young colleague Ibrahimova, we considered the case, we have considered the case of the oscillating dark matter. And for doing this, we consider the Poisson equation with rho dark matter. And dark matter we also considering as a plane wave. And Jeans equation, after some natural, physical, and mathematical transformations, is possible to reduce to this equation of the second order, very simple. And what is the physical result? Physical result is as follows. From our searching, we found that if we are considering two oscillating substances, from one side this is baryonic matter, from other side this is non-baryonic matter, and after their interaction between themselves may be number of physical processes. One of them, this is pressing or depressing one wave. For example, dark matter may depress oscillations of baryonic matter, but it is possible to consider another case when baryonic matter depresses oscillations of non-baryonic matter. In other words, you see that it is possible to find different cases that are describing the process of interaction between these two substances. Of course, if we are considering both of them as oscillating ones. So maybe our idea is not real. Maybe this idea is very strange, but we found in literature number of articles where authors also considered oscillating matter as dark matter as the oscillating matter. In this slide, you see number of authors. It is possible to consider these articles as recent articles. This is, you see, this is one of them. This is Marek Kamienkovsky. That also he's one of the most active scientists in the sphere of searching oscillating dark matter. That is why we are considering that it is possible to consider the dark matter as the oscillating substance. So in this slide, you see some problems that we plan to search. What are these problems? I'll explain very briefly all of them. This is, first of all, we are considering dark matter at the scalar field, and the simplest case is the harmonic or considered in the following article. Another case what we plan to consider, this is a modified or more complicated case of the potential energy of the scalar field. This is UF that is proportional to F in nth power. And for this case, it is possible to find the omega, the relation between density and mass density and the pressure in this form. Next time I talk with it is possible to say he is my friend, my colleague. This is Eric Linder. In this article, he considered a more complicated expression for omega. In this case, you see omega. This is constant also, but in principle, it is possible to consider the omega as variable constant. In this case, you see that it depends on the redshift, but though this expression has been introduced for searching the dark energy, but of course it is possible to use this expression for describing the dark matter also. And next step, we are considering the more complicated potential energy of the scalar field that includes not only phi squared but phi in fourth power, and another potential that depends on the hyperbolic cosine on F. So I have enumerated number of problems that we want to consider. If we know if we find the potential of the scalar field, it is possible to construct the tensor energy momentum tensor for the scalar field. If we know the tensor of energy momentum, it is possible to, of course, find its rho, its pressure, and so on, and use it for describing the oscillating dark matter. And one more problem that for me it is very interesting. The problem is as follows. At the beginning of my talk, I said that, well, everybody knows, of course, but I'm repeating once again that galaxy consists of baryonic matter and non-baryonic matter. But the question arises, why baryonic matter concentrate in the center and non-baryonic matter surrounds baryonic matter? In principle, this is not a very trivial question, and it is possible to consider as follows, to search this problem as follows. From number of scalar fields that describe the non-baryonic matter, especially in the case of early universe. For this case, authors found that particles that describe this dark matter is heavier than neutrinos, and this is very important, heavier than protons. This means that from our vision, this means that mass of particles of baryonic matter becomes smaller, and this is why, due to the centripetal force, more light particles, of course, will tend to the center. And this idea have been come up to my mind, and after this I found article where Germanian astronomers, due to the simulation, describe this process. You see, this is, in this slide, you see that dark matter only, different variation, different regions of dark matter, it is possible to describe as in the form that rho of dark matter depends on the distances. This is known result, but in this case, you see, this is dark matter plus baryonic matter, and baryonic matter, namely, concentrate in the center of this object that we are considering as a galaxy. And of course, we want to search this problem more precisely, and especially in the case when we're considering the dark matter, the oscillating one. That is why I say about some problems that we plan to consider in the case when dark matter is oscillating matter. And this is final slide in which you see that we thank you for our attention. That's all.
Some questions or comments?
Хорошо. Хорошо.
Professor Chechen,
yeah.
when you look at the spatial dependence, so you have your time dependence, your oscillations, and your spatial dependence, do you restrict to spherical symmetry?
Yeah. At the first, this is first the most simple variant when dark matter forms. This is a spherical one, of course. Of course.
So I'm thinking that galaxies, at least spiral galaxies like our Milky Way, they have flattened disks as well as spherical halos. Yes. And it would be interesting to see what your model predicts.
You're quite right. Because we know that every galaxy possesses its own rotation. And the question, of course, arises, what is the physical reasons of this rotation? But there are some physical mechanisms for example, due to the gravitational interaction. But nevertheless, the most very important question arises, what is the physical reason of the initial rotation, initial physical mechanism? And this maybe due to the from our viewpoint, as minimum, due to the two physical reasons. First of them, if our universe rotates and it passes its momentum to objects that introduce in the our universe, this is a well-known approach. And the other side, from other side, this is pure relativistic effect. Pure relativistic effect. By the way, this effect have been discovered in Kazakhstan, in our university. Its physical essence is as follows. If we are considering general relativistic equations of motion, everybody knows that this equation is divided into two parts, translational one and rotational one. And from general relativity, if we are considering this or problem of motion from general relativistic approach, it is possible to find the following. If body moves without rotation, it becomes to rotate. This is pure relativistic effect, general relativistic effect. In other words, the movement, translational movement, transforms to the rotational one. And because every galaxy possesses a right movement, different peculiar movements, and so on, and that is why it must depend. It must possess initial rotation, initial moment, and this has been found by our teacher, academician Abdildin, and he was the student of academician Fogg, and so on. But I try, if you remember my previous report, more than 1 month ago, I tried to applicate these equations to the universe as a total one, not only for objects such of galaxies and so on.
So my question is rather simple. So my question is rather simple.
I understand.
So, if you have dark matter oscillating,
Yeah.
so what is the characteristic time scale for oscillation?
Now I couldn't answer this question because we, with my colleagues, young colleagues, we are only try to find the way for searching for searching this problem, and maybe the simplest case, if we will consider a phi potential of scalar field, that may be periodical function, and at the first slide that I shown in my talk, I try to find or explain the physical reasons of these possible oscillations. This is oscillation or two galaxies. Moreover, truth consists of number of particles. They are, in principle, as baryonic matter. Non-baryonic matter as baryonic matter may be considered as the oscillating one.
Thank you. Any questions or suggestions? Okay. Just thank you, Professor Chechen, for your presentation.
Okay.
Okay, let's start with. And the second presentation will be of Professor Yunus Aliyev. He's from Kazakh National University named Al-Farabi. So the talk will be the simplest nanoscale generalization of supersemester and cosmology constant. So.
Тогда зачем вот этот? Мне же
Ну, надо же ваш экран показывать.
Не, у меня на
So we can start and maybe.
Вот ваш экран показывает.
Oh,
Окей, нажмите. Все, право влево и...
Okay.
Devoted to some non-associative correction to the supersymmetry generators and how it can be connected with cosmological constant. So now we know that we live in the expanding universe. The expansion is with acceleration. So the origin of such acceleration is so-called dark energy. So we have many dark energy models. For example, quintessence, K-sense, Chaplin gas, modified gravity, brain cosmology models, and so on. So, but only one model is this model. Maybe that in this model we will have some new fundamental constant, which is cosmological constant. Dynamic. That in the sense that for every such model we have to have some equations of motion, Lagrangian, Hamiltonian, and so on. So, and for me it's interesting to consider the possibility that lambda is indeed a fundamental constant, and what is interesting, what kind of physics is behind such approach. So this is idea that cosmological constant lambda can be connected with appearance of non-associativity in physics. This is very standard physics. Nevertheless, I want to show that it's possible to take such generalization of SUSY. So physical, in this case, the physics is that constant lambda controls the smallness of non-associative effects in quantum physics. So I will show the dimensionless quantity square of Planck length times to cosmological constant, which is has such 10 to the minus 120, shows that non-associative effects may occur, but in very small region. It may happen either on such huge scale, that is the scale of our universe, or maybe with some small moment of P0, which is connected with L0, H divided on L0.
Sorry to interrupt you. Could you please explain what is non-associative effect?
Yes,
what do you
right.
mean by this?
So 2 or maybe 3 slides later. So now in this slide, I want to compare appearance of non-associativity with appearance of non-commutativity. So we have such chain. So we have classical physics. So in classical physics is commutative and associative. If we want to break commutativity, we have quantum physics. And breaking of commutativity leads to the appearance of Planck constant H. But what happens if we want to break associativity? So I will show that in this case we will have some dimension constant with a dimension of centimeter. So in this case we will have some new non-associative physics, and only what we have to have that such breaking of non-associativity should be very small.
Very small, what does it mean? Very small?
10 to the order minus 120. So this is, yes. So this is dimensionless quantity which can be constructed from Planck scale and cosmological constant. Yes, so in this slide, let me compare breaking of associativity with non-commutativity. If we want to obtain some non-commutative physics, I mean quantum physics, so we have to write that it is well-known standard relation between x and px, so it should be IH. So what the physical sense of this, that x and px are non-commutative. So now I want to explain what is it non-associativity. Non-associativity is if AB times C is not equal A times BC. So I want to show, so my talk is, I want to show how it's possible and what kind of constant will appear in such case. So main idea of this model is that generalization of associative supersymmetry to non-associative supersymmetry leads to the appearance of a new fundamental constant that has a dimension centimeter or centimeter to the minus 1. So let me, so I think that this and this next slide is key slides in my talk. So let me first of all remember what is it SUSY. Key idea in SUSY that we have some generators Q, and anti-commutator of such generators gives us P, which is minus IH partial derivative d mu. So I want to, so we can generalize such expression to including some additional term to this operator Q. So in this case, this Q will be tilde Q. So generalization is can be made in such way. So Q is standard Q from SUSY, and Q1 is non-associative term. So and Xc is this small number. This is L Planck divided on L0 to the 1/3. So in this case, generalization of anti-commutator in supersymmetry has such form. Tilde is something non-associative. So if I consider the simplest way to generalization of supersymmetry, so I will obtain such associator. So how we can obtain such associator? So it something like commutator in quantum mechanics. In quantum mechanics, we have on the left hand side xp, on the right hand side without any operator. So on the left hand side we have two operators. 2 minus 2 will be 0. So here also the same idea. 3 minus 2, I have one operator on the right hand side. So and if I want to, in order to simplify such expression, I will apply Jacobi identity. So and after that, I have such expression where L0 is some constant which equalize dimension of the left-hand side and the right-hand side. So L0, so it's very easy to calculate the dimension of L0. This is centimeter, and so main idea is it's L0 is connected with cosmological constant lambda to the minus half. So why L0 is connected with cosmological constant? So the reason is that I have to, sorry, I don't know why. The reason is that so non-associativity should be very small. Only in this case. So this ratio will be very small, negligible. Okay, so yes, but so this the reason for the main idea of this model is have some additional mathematical arguments that lambda is fundamental constant. It is not some dynamical field.
So you are not you take into account this term.
No. I know. So only what I want to do that I want to show that if you want to generalize UZ to some non-associativity, so you have to introduce some constant. This constant should be very small. So I connected with lambda.
Sorry for one more question. Why you choose zero? Why for searching L0? Why you choose the cosmological constant? Why?
I don't have any other constant with dimension centimeter. H, C, G has different dimensions. If L0 is sorry.
I see.
If L0 is okay, of course I can connect L0 with Planck constant, but in this case non-associativity will be very big. So I want to have very small non-associativity. So okay, so and how it works? So in this case, if non-associativity there is in physics, then we have some maximum length L0, or I want to say about minimal four-dimensional scale curvature because it's only unicolored invariant quantity having dimension centimeter to the minus 1. So and this is very simple explanation for the acceleration of the present universe. The universe reaches the minimally possible curvature and has to stay in this state. So it's not all. So it's interesting that such approach. So this is mathematical physics. Now it's mathematical physics. So it is interesting that in this case we'll have some interesting mathematical consequences. For example, if I consider only small non-associative correction in such way, then I have some connection with so-called generalized uncertainty principle, which is doubly special relativity, and Q-deformed algebras. So I can choose my associators in such way that commutation relationship between X and P will have some additional terms. So this is doubly special relativity. And I can choose associators in some another way, and I will obtain Q-deformed commutator. So Q-deformed commutator is by definition such difference. So it's equal as usually IH delta mu. So what in this sense, what is interesting for mathematical physics that one can say that non-associativity, there is some some very complicated algebra in mathematical physics maybe have something simple explanation from non-associative point of view. So in my conclusion that one can introduce non-associativity into SUSY. That means that generalized SUSY. Breaking of non-associativity leads to a new fundamental constant with dimension centimeter to the minus 1. So I think that this should be connected with lambda because only in this case we will have very small NA effects. So and small NA correction appear in Heisenberg authority principle is as generalized authority principle or as Q-deformed commutator. So thanks for your attention.
Any questions or comments? Okay, just can I give to our students?
Thanks for the talk. It's not clear to me yet where does that non-associative feature comes from.
Sorry.
Non-associative, you said. Non-associative feature. Where does it come from? Why do we talk about it? Why do we care about it?
So only one idea. I want to show that there is some mathematical arguments that lambda is indeed a fundamental constant, not a dynamical field, like Chaplygin gas or K-sense or something like this.
You introduced it as a method in order to prove that lambda is indeed a fundamental constant.
No, it is not proof. It's not proof. It's only idea, only model.
All right, I got it. But this is like a method of approaching the problem. You introduced it, come to the problem from the non-associative way.
Yes.
All right.
Yes.
Makes sense.
I can add that. So on the second slide, you see that we have many models of dark energy, and only one where the lambda is fundamental constant. So and maybe dynamical fields as models of dark energy are not very good because they should have some evolution in the time. And this is the first one. The second one is that up to now, what I know that the best fitting of experimental data is lambda CDM, when lambda is constant.
But there are no,
No, it's okay.
But there are, we know that there are, I can say a vast number of articles where lambda have been considered as the variable in time.
Yes.
This is
Yeah.
maybe your
It's
tendency.
not the proof that that is true. It's only some idea, some model. Again, it is only some mathematical, once again, mathematical arguments that if lambda is fundamental constant, that maybe behind of such constant there is some NA physics. It's not the proof.
Who knows?
It's only idea.
Okay, so let's imagine that we could reproduce this small value of this cosmological constant.
Yes.
So, but you broke the associative law, and this should have some consequences.
Yes,
What are the
right.
side effects?
Right, exactly. But so I choose L0 as lambda to the minus half in order to have very small NA effects. So these effects are 10 to the minus 120. So it's not possible to see such effects. in our real physics.
I mean that these generators are related to conserved charges, as I understand.
Q
Yes.
Q are
What else?
SUSY generators.
SUSY generators.
So
So you have this non-associative operator, let's say charge.
no, Q originally Q coming from supersymmetry. So here I consider some small additional terms for Q.
Yeah, and okay. So does it have any effect on the physics? I mean, you have cosmology constant on one side, but you have some additional piece in the generator, which should change the physics that generators encode.
So the change is for the appearance of the middle constant lambda.
Well, you are just concentrating on the lambda, but there should be.
Yes, right. So that's right. That's right. It should be some, of course, should be some additional physical effects in such case. But I think that such effects are very small. So once again, I want to say about some idea, some mathematical arguments once again about why is it, if it's constant fundamental, then why?
Okay. Okay. Any questions or comments? If not, okay. Thank you, Professor Junashali, for your presentation. It was very interesting. So now we have a time for discussion, and there section is discussion with Professor Khazoomi, Professor Linder. Just we have some guests from Almaty, like Abishev, Professor Abishev Medeo, or Professor Takibayev. If you have, maybe you let's just introduce yourself, introduce your group, which came from Almaty, and we can see what your team or professor Abishev will do it. Also, we have some guests from Asil Turgen Observatory. Also, maybe they give some. They gave the talk tomorrow about their observatory, about their place. But maybe some words will be included today. We can say something about your team. Just I don't know. Can you start, or then Professor Abishev, or you want to start the first?
Good evening. It is we are from Almaty, from university, the biggest university in Kazakhstan and oldest also. It is the Al-Farabi University. Al-Farabi, it is a very famous scientist in Middle Asia, and mathematics, and working together with another famous scientists in 11 centuries, 11, 12 centuries, etc. And he give the name of South. It's very interesting. And with Avicenna, etc., they working together. And of course, if we have so famous scientists from Kazakhstan, from this earth, from our side, our university, very proud that his name have in our university, and our students also take the behavior that strong working and it's other things. This is our students, and this is our younger chair, head of our chair, and it is from astronomy institute. There we working together sometimes, etc. And our university provide about 7, maybe 10 workshop and conferences in year, and 2 of them very big, like Al-Farabi conferences theory and other things in physics, and of course in medicine and chemistry, etc., etc., etc. And we are proud to visit Nazarbayev University, and a very nice and very skilled scientist and leader in your countries and community of science. And thank you for your hospitality, etc. And my report tomorrow morning. And I invite you to visit us. Okay, thank you very much.
Thank you for
I'm
you.
sorry.
Just maybe Professor Krugov will just give some introduction about your team.
First of all, I'd like to thanks for so informative day, where usually not so often came to theoretical part, because we're observer people from observatory and usually working with telescopes and instrumentation. Not nighttime, daytime, every time. Yeah, 2 weeks before we receive a first light from 1.5 meter telescopes at Turgenia Observatory. 25 years it was stopped, and now we're thinking about which project it's need to implement there. And then for us, we're 100% knows about that there is need spectrograph works, but maybe some of polarization, some of photometry. We will think about that. Yes, and thank you very much. If it will be some of interest in some people interested of territory of Kazakhstan observing, we're fully open, and we're working with worldwide telescope program in Arizona University, and some of the American and Germany's programs too. But we need to grow in our astronomy potential for own program, which we can support more fast. Yeah, thank you.
Thank you so much. Okay, it's what is there in this. Also, we have. Do you want to add something? It's okay. Maybe just okay. Do you want to tell something? Okay, because he did it. Okay, we have also a professor from Nazarbayev University.
My name is Vasilios Zarikas. I'm a new faculty member in the School of Engineering. My field is applied mathematics, but I perform research in cosmology. I collaborate with the University of Thessaloniki in Greece, and I'm doing baryogenesis, neutrino physics, and with the university in Aegean Sea. There we are doing cosmology, modified gravities, and last years I'm interested in asymptotic safe gravity. And here I also work in mathematical modeling for engineering problems. So I enjoyed a lot this seminar today, and I will follow tomorrow closely your work. And I enjoyed very much your talks.
Thank you so much. Thank you so much. Okay. Also, just I want to give some microphone to our active students, because you put many questions. So please introduce yourself.
Thanks everybody for coming. My name is Maghjan Kistobayev. I studied in Kazakh National University named after Al-Farabi for 3 years, Department of Nuclear Physics. And then I dropped it and then got my undergraduate in the Pennsylvania State University. Now I'm doing my science degree in masters in physics, not in engineering, which is really tough. I have to admit it. It's been like 3 months since I started doing astrophysics, and it's really tough subject, but it is as hard as it is interesting. So the hardness escapes if you're getting interesting. So thank you all for doing this wonderful thing, exploring and then sharing your knowledge with us. It's an honor, it's a privilege, and it is a joy. Thanks.
Oh, thank you so much. So really warm words for us. We need it. Yes. Or maybe I don't, who else want to say? If not, okay, I'll just want to say thank you for everybody, for Professor Linder, Professor Hazumi, that you all came to Nazarbayev University, because it's very important for us. We just start this project itself, so we found like Dr. Smooth. It started maybe couple of the 2 months. So just, and we're like happy that you will visit. You're our first visitor. Yes, we are very happy that you came to us. So just what I would like to thank you for Professor Linder, because he's every time support us. Thank you for you. Also, I would like to thank our like Almaty team, because thank you that you were like every time inactive for us when we just say please come to us, and you say okay, we will do that. Thank you for your participation. And what I would say, let's see you tomorrow morning at 9:30 a.m. at 9 block BG room, that we have some talks of Professor Maxim Krugel. He will talk about the observatory. Also, we have some talk of Professor Takibai. He will give some introduction about his research. I think maybe Bruce Grossan, one of the like leadings of our ACL group, will also participate in the morning session. So, okay, thank you for everybody. Oh, sorry, yes, and sorry about that, yes, and Professor Chechen will give some, maybe 10 or 50, how many you want, okay, give some talk about the like introduction, yes, like the introduction of, yes, gravity, you said, say this. Okay, see you tomorrow, and thank you for your participation.
Thank you.